गणपतिं महागणपतिं 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 सुतं गुरुगुहानुतं महादेवसुतं गुरुगुहानुतं महादेवसुतं गुरुगुहानुतं मारकोटि प्रकाशं शान्तं महादेवसुतं गुरुगुहानुतं महादेवसुतं काव्यनाटकाधिप्रियं महाकाव्यनाटका महागणपतिं मन.
Thank you, ma. Sir, Chairman of the conference.
Shall I stand here or there? To this two-day international conference on resilient innovations for subsistence environment, IC Rise 2025. At the outset, and today's Dr. N.V. Ramakrishna Garu and my colleague Dr. N. Venkateshwara Garu, Principal, and today's conference convener Dr. Srinivas Garu, HOD, Department of Chemistry of this college, and two other prominent persons. One is Mr. Sridhar from Chemistry Department and Dr. Tejashwini and Venkateshwara Garu from Control of Examinations, and our eager, YRC District Committee Convener, Dr. Suresh, Professor Shivakumar Garu, and in front of the stage many chemistry faculty from different departments, from different colleges across the country and across the state. It is not exaggerated to tell like this, and this is the second international conference for this academic year. The first international conference conducted by from the same DST SERB here IC Rise, and the next year indication of that the Department of Chemistry is very strong echoes and all. Environment is the prime and more series of conferences and enlightening the students and public somebody's property to destroy, and that means if we are living from dawn to dusk and entire this human life, so how can we protect these things? So environment is a very prime thing for us actually. So that means how can we reduce the greenhouse gases, like UN United Nations constructive statement of that they are going for reducing 12% for their uses of the clear fortune to work on this environmental protecting research method of CO2 reduction. How can we break the CO2 molecule, environmental sustainable practices at USA, and then as a comeback project also, and some scholars are working in my laboratory right now. 10 lakh Rusa as far as green synthesis to make some nano composites, and we are going for some. Right now the college is 24 research projects were given by me as a internal resources to inculcate research atmosphere and a taste of this preliminary results and research, and they are going for outside funding also. So that is the motivation behind colleges. Last year we have got 200 plus publication, 215 like this component to get NAC accreditation, reduce, reuse and recycle. So this is a very good triple R, a slogan for a science and arts and a common man too. So dear students and scholars and eminent personalities on this stage, So I would like to end my message. All, as a physicist, we are all fan of Einstein. Okay, the Einstein is always telling that means energy may be converted into mass, mass may be converted into energy when the body goes to square of the light velocity. This here, instead of energy, you can think of environment. So environment is equal to just some kind of M for motivation and C for a care and concern. Square of the care and concern, and you need to have a motivation, you can protect our environment. That's what I want to give you message by dear young students and all. Thank you for giving the wonderful opportunity. Once again, heartfelt thanks to Department of Chemistry for...
Thank you very much for your valuable and inspirational words. Now I request...
Very good morning to each and every participants and as well as to Department of Chemistry taking so much of pain for conducting this, but to each and every
words on this occasion.
So, to speak something, to give something us, to give something us. Today is a really a blessed day. Really a blessed day, a wonderful day, a day of learning, a day to know something innovative, a day to inspire someone, a day to inspire someone. Today we gather not only to highlight challenges, but to reimagine solutions, resilient innovations. So this is మైన రోజు. మనం చాలా గొప్ప వ్యక్తుల ముందు వాళ్ళ ఇండియా ప్రైడ్ సైంటిస్టులలో ఒకరు మన ప్రసాద్ గారు. వారు మన ఆహ్వానాన్ని మన్నించి ఈరోజు మన కాలేజీకి రావడం చాలా గొప్ప విషయం. అదేవిధంగా ఇక్కడికి వచ్చినటువంటి ప్రతి ఒక్క రిసోర్స్ పర్సన్స్ అందరూ కూడా చాలా గొప్ప స్థాయి వ్యక్తులు. సో నా యొక్క కన్వీనర్గా నా యొక్క రిక్వెస్ట్ మీ అందరికి కూడా ఏంటిదంటే ఇది మీ అందరి కోసం. ఎందుకంటే ఎన్విరాన్మెంట్ ఈజ్ అవర్ మదర్. మనకి అమ్మ ఎవరంటే ఎన్విరాన్మెంట్ వల్లనే మనకు ఫుడ్, ఎన్విరాన్మెంట్ వల్లనే మనకు రక్షణ, మన ఉనికి, మన ఎగ్జిస్టెన్స్, మన ఐడెంటిటీ, ఎవ్రీథింగ్ మన ఎన్విరాన్మెంట్. దాన్ని మనం రక్షించుకోవాలి అనుకుంటే మనం ఇటువంటి అనేక ప్రోగ్రామ్స్ జరుపుకోవాలి. అందుకే డిపార్ట్మెంట్లోని దీని నుంచి గొప్ప విషయాలు మిగతా వాళ్ళకి చెప్పి ఆచరించాలని కూడా కోరుకుంటూ ఈ అవకాశం ఇచ్చిన పెద్దలకు కృతజ్ఞతలు తెలియజేస్తున్నాను. థ్యాంక్ యూ.
Thank you very much, sir, for your valuable words. Now I request our beloved Guru, Sri Dr. M.V. Ramakrishna Garu, to speak a few words on this occasion.
Respected RJD Zone 1 and 2 Rajahmundry, Santishwar Bhatnagar awardee Professor K.R. Prasad Garu from IISc Bangalore, convener of the symposium Sri T. Srinivasa Rao, HOD Government College Rajahmundry, distinguished guests on the dais, learned faculty members of the chemistry department, and student friends. International seminar on resilient innovations of our subsistence environment, useful to all of us. Just like in just only పడుతుంది. అలాగే ఎన్వైరాన్మెంట్ని మనం కనుక రక్షిస్తే ఎన్వైరాన్మెంట్ మనకి కాపాడుతుంది. కాబట్టి ఐ అడ్వైజ్ యూ ఆల్, అంటే వినేసి వెళ్ళిపోవడం కాదు, డూ ఇట్ ఇన్ ప్రాక్టీస్. బోర్డుని చెప్పాల్సి చాలా ఉన్నాయి. యునైటెడ్ నేషన్స్ ఎన్వైరన్మెంట్ ప్రొటెక్షన్ వాళ్ళు ఇచ్చినటువంటి రూల్స్ అన్నీ చెప్పచ్చు, కానీ ఇప్పుడు టైం లేదు అవన్నీ చెప్పడానికి. ఇవన్నీ కూడా మీకు ఒకటే నేను చెప్తున్నాను, జస్ట్ కనుక్కోండి అంతే. యుఎస్ఏ పెడుతున్నారు, తల్లిదండ్రులు అందరూ పెడుతున్నారు పిల్లల దగ్గరికి. ఎంత జాగ్రత్తగా ఉంటారు. చిన్న తుక్క అక్కడ పడేస్తే $100 ఫైన్ పెట్టి ఐ గాట్ ఎవరి రైట్ టు త్రో ఎవ్రీథింగ్ ఆన్ ద రోడ్, అంతే కదా. రాజమండ్రి రోడ్ మీద మనం పడేయచ్చు, ఫైన్ వేసారు అనుకోండి వెంటనే కూడా కొడతాడు కూడా మనం పట్టుకురండి. కాబట్టి అమెరికాలో ఫైన్ కడతాడు, ఇండియాలోనేమో పడేయచ్చు. కాబట్టి మరి అది కాదు కదా పద్ధతి. యూ ప్రొటెక్ట్ యువర్ సెల్ఫ్, ఎన్విరాన్మెంట్ ప్రొటెక్ట్ చేయండి. తెలిసే ఉన్నాయి అన్నీ కూడా. మొత్తం వాటర్ లీటర్ బాటిల్ ₹50 తీసుకున్నాడు, మనం తిరిగి ఆ బాటిల్ తిరిగి ఇచ్చేస్తే ₹30 తిరిగి మనకి ఇచ్చేస్తారు. అంటే ₹20 లీటర్ బాటిల్ మామూలే కదా. కానీ ఎక్కడా కూడా టోటల్లీ ఉన్న హిల్స్ మీద చూసేవన్నీ కూడా. కాబట్టి యూ ప్రొటెక్ట్ ది అట్మాస్ఫియర్, కాపాడుకోవాలి. కాబట్టి విత్ దీస్ ఫ్యూ వర్డ్స్ జస్ట్ ఐ సే ఫ్రమ్ IACR ఆర్ ఫ్రమ్ IAC బెంగళూరు అందరూ కూడా ఇదే కాలేజీలో BSc చదివిన వాళ్ళు, ఇదే కాలేజీలో MSc చదివిన వాళ్ళు, 5 సంవత్సరాలు ఈ కాలేజీలో చదివిన వాళ్ళు అందరూ రేపు ఆన్లైన్ లెక్చర్స్ అనుకోవచ్చు ఫ్రమ్ USA. అట్లాగే మిగతా బయట నుంచి వస్తున్న వాళ్ళు కూడా అది రేపు.
On the dais, Professor Prasad Garu, Shanti Swarup Bhatnagar Awardee, the President of College Principal Garu, Dr. Ramchandra Rao Garu, a dynamic, young, vibrant, great leader.
Now I would like to invite Dr. Professor K.R. Prasad Garu to keynote address. Before that, Dr. Mallikarjun sir will introduce the sir.
I extend warm welcome to my co-principals, Dr. Sunita Madam from Chemistry Department, and also Dr. Srivaram Garu, Chemistry Department. Earlier they worked here in different capacities in this college. Hearty welcome for the conference. Thank you. Dr. Ramarao Garu, who is that? He's my colleague and friend. He also hailed from long place to here. Hearty welcome to Dr. Ramarao Garu too. Thank you.
And passion for advanced research in organic chemistry, he broadened his horizons through the prestigious international fellowships. As an Alexander Humboldt postdoctoral fellow, he conducted pioneering research in organic chemistry, University Münster, Germany, 1998-2000. He later continued his postdoctoral work at the Department of Chemistry, Temple University, USA, 2000-2003. Continuing to cutting-edge research in synthetic organic chemistry, he also briefly served as a research scientist at Precious Pharmaceutical, USA, enriching his expertise with industry-oriented scientific perspectives. Professor K.R. Prasad sir joined the Indian Institute of Science, Bangalore in 2003, where he has since built a remarkable academic legacy, ranging from assistant professor to associate professor, and currently Professor K.R. Prasad sir serving as a senior most professor in the Department of Organic Chemistry. He has spent over 2 decades nurturing the scientific talent and leading transformative research at one of the India's most prestigious institution, that is Indian Institute of Science, Bangalore. His research group at IAC, internationally recognized for excellence in total synthesis of complex natural products, particularly those of therapeutic importance. His work elegantly integrates the development of asymmetric synthesis methodologies, chiral sulfamine chemistry, and the synthesis of biologically active alkaloids. So there are a lot of different fields are there. Sir is covering all that. So sir at now published 120 research publications in reputed international journals. Sir received so many awards and honors. Professor K.R. Prasad sir, scientific excellence has been recognized through numerous prestigious awards and honors. He is a fellow of Indian Academy of Sciences 2015. Sir is a respect of Santi Swarup Bhatnagar. Give a big round of claps. That is, sir received Santi Swarup Bhatnagar Award in 2014, and recently sir is also awarded J.C. Bose in 2024. It's a great time to have the Prasad sir here. And also received, sir, he is currently served as a associate editor of Organic Letters, one of the most respected journals of the American Chemical Society, and accolade reserved for the leaders in the field. Today, we have privilege of hearing from scientists whose work inspires students, researchers, and professionals across the globe. A visionary chemist, dedicated mentor, and luminary in organic chemistry. Ladies and gentlemen, please join in welcoming our keynote speaker, Professor K.R. Prasad sir, to deliver his address. Thank you, sir. Thank you so much. With this brief introduction, I invite Prasad sir delivering his lecture.
లేదు దీంతోనే చెప్తాను.
ఈ లైట్స్ ఆపేయాలమ్మా. లైట్స్ ఆఫ్ చేయాలి. అది అక్కడ ప్రజెంటేషన్ మోడ్లో పెట్టేయండి.
డౌన్లోడ్ చేసావా? అడోబ్లో ఓపెన్ చేస్తావా? అడోబ్లో ఓపెన్ చేసి లేవా మీకు?
ముందు స్క్రీన్ కనెక్టివిటీ ఇవ్వాలి. స్క్రీన్ కనెక్టివిటీ
వస్తుందిగా, స్క్రీన్ వస్తుంది.
దీనికి రావడం ప్రాజెక్ట్ రాండి.
All of you keep silence, session will start. Please.
పాయింటర్లు ఏమైనా ఉన్నాయి నాయన? పాయింటర్ ఏమైనా ఉందా? హలో, గుడ్ మార్నింగ్. హలో, గుడ్ మార్నింగ్. ఇది how do I change it? Change the slides. Okay, fine. Good morning everybody. Can you hear me? Can you hear me? Thank you. Good morning. So it's the opening batsmen always have the trouble. Eh? And I keep the pitch ready and the others will bat properly. Right? Interesting. So thank you very much for the invitation to be here. I was told that there is no pointer. I also did not bring, thinking that you people will have it. Please, can you? This is one of the nuisance at the airport, because they will say remove the battery and all that. So I thought you people might have it. So anyway, please, you are a nice guy. You have to switch it on somewhere, no? That boy is nice, huh? Wonderful. All right. Okay. If you are comfortable me speaking in Telugu, please tell me. You are comfortable 75% English, 25% Telugu, or the other way around, that also you tell me. I am comfortable, no problem. Okay? So thanks for the invitation, Srinivas. One of the main reasons why I am here, I must tell you, is all because of Dr. Ramakrishna Rao Garu, who has served your college for a long time. And he was instrumental in sending several students for research purpose to our institute and to other institutes, and then always in touch with us to see whether how we can do something good for your college, right? Thriving for that rather than, not working for that, but always trying to see how we can do some improvement, right? So when he insisted, or when he asked, we could not refuse, so we are here. Anyway, since your college was established in 1853, I thought I will talk about the history of organic chemistry rather than our own research work, and try to connect from those days to present days. So that's why I've given a title from Wöhler to the current state of the art. Okay? It's good to read about history. At the same time, it's not that we have to harp on history, but we should progress further. Okay? In the next 45 minutes, I don't want to be between you and your lunch. So I will try to be as concise as much I can, and I will try to see that what best I can impress upon you. Since I was told that the lecture would be for students who are in BSc and MSc, I tried to give as many textbook examples as you can see, okay, and trying to connect it in the research perspective. All right? So, what is organic synthesis? That is something which has been, is it better I go there? Yeah, okay. Okay. So, most of you learn organic synthesis as to connect the carbon-carbon heteroatom bonds. And in connecting those bonds, you always have a control element. If you don't have that control element, the bonds get connected randomly on its own will and wish, and then you will not have the architecture what you want. So, to have that control element, which you call in chemistry terms the selectivity. The selectivity starts from simple regioselectivity, chemoselectivity, stereoselectivity, enantioselectivity. It's, for example, if you synthesize a olefin, how you can synthesize the E olefin and the Z olefin. If you are doing it, if you want to make one chiral center, then how that would be? Can you make it enantiomerically pure? If you are having two centers, can you make it diastereomerically pure, and then that can be enantiomerically pure? And then chemoselectivity, that you don't want to change one functional group, but then you want to do reaction at other functional groups. For all this, you require control element or an understanding of the reactivity of the functional groups. And then you should devise the synthetic method in such a way that you effectively transform that functional group only, and that too with precise selectivity. This is something which most of us organic chemists think about it. And in that process, when you're having the thought of designing a molecule, you need to design first. Everybody can design many things, but then you should have the execution skills. That execution skills comes into picture only when you have a thorough understanding of the reactivity of functional groups and the CC bond forming reactions or C heteroatom bond forming reactions, or in general the reactivity of the functional groups. If you don't understand the reactivity of functional groups, you would not be able to make this molecular architectures of the molecular assemblies. So, it started with urea. This is 1835, yours is 1853. Just 18 years before your college started. Yeah, we didn't even have the first mutiny also. Right? Wohler, when he made urea in 1828, he wrote to his supervisor, Liebig, that I could make urea from, from different inorganic substances, or you don't need to have the kidney of man or dog or some animal. From those days, it used to be isolated from human urine also. And then the organic chemistry thought that you need to do something from a living substance, or living human being or dog or animal or anything, something like that only. But at that time he predicted that this would be a subject which would be very different, and it would grow into such a thick forest-like field, and you would not like to enter into that. That's what the statement Wohler felt. But then if you look carefully, what Wohler did, Wohler took ammonium isocyanate and then heated it to get to urea. How do you make it? You take silver isocyanate and ammonium chloride, you get ammonium isocyanate. But there is another one that's called silver cyanate. If you change the oxygen to the other side and carbon here, you can have it. That is silver cyanate. And this is silver fulminate, that is CNO bond, and this is something which was studied by Liebig. Now, by changing the nitrogen, carbon, oxygen positions, you can have three different substances. At that time, Wohler doesn't have a concept of isomerism, mind you. It so happened that he took the silver cyanate, ammonium chloride, made the ammonium cyanate, and then heated it to give urea. What's very interesting, that if you look at the number of carbons, nitrogens and oxygens in the starting compound, and if you look at the number of carbon, nitrogen, hydrogens and oxygens in the product, both are one and the same. Nowadays, people call it as atom economy, means you are not taking so many things, you are not generating so much waste, and you are just heating it, so you don't require so many other reagents. So it's a green synthesis and all that. The birth of organic chemistry itself is green, because you just take ammonium acetate and heat it, you get urea. When Wohler did this, people were surprised. Oh, you can make organic compounds from materials which are available. Till that time, we believed that, as I said, you can make only from the living objects. That's not the case. Then people were trying to see that really, can you make organic compounds? Kolbe came into picture. But some of the material, by the way, let me acknowledge, some of that I have taken from internet, and some of them which our own research is not from internet, it's from our group. What Kolbe thought is, let us think like this, if I give you charcoal and ask you to make acetic acid from that, in today's context, you will ask me that I have gone mad and why should I make acetic acid from charcoal. I give you charcoal. Charcoal, you know, right? If I give you charcoal and ask you to make it acetic acid, a liquid, you think that unless I have a magic wand, I cannot do this. But Kolbe was somebody who wanted to do some kind of an organic chemistry. He wanted to prove that you can make organic compounds from non-living objects. He took charcoal and then he heated it with iron sulfide. Then you get carbon disulfide. This carbon disulfide he treated with chlorine to give you carbon tetrachloride. Can you check this? Can you hear me? It's okay? All right. I don't know. You can bear with me. So carbon tetrachloride, he heated it to get tetrachloroethylene. That tetrachloroethylene he did pyrolysis in presence of oxygen to get trichloroacetic acid. The trichloroacetic acid he reacted with hydrogen to get acetic acid. It might look very different for us now, but you should appreciate the fact that somebody was trying to synthesize an organic compound called acetic acid with carbon, oxygen, hydrogens present in it from charcoal. This is when your college started. I correlate all the time the advancement of organic chemistry to us. So at certain time we should question ourselves where we are, where we were when the others are progressing. So he took charcoal, and this is what you read in textbooks, in the sense you will read in textbooks that you take carbon and then heat it with iron sulfide in presence of hydrogen, you get acetic acid, coal-based synthesis of acetic acid. This is very different from coal-based synthesis of salicylic acid. That's afterwards he has done. This is another landmark, if I can say that this is total synthesis of acetic acid from charcoal. You can say something like that. Okay. When these things are progressing, in Germany there were people who were looking at organic chemistry at a different perspective. People were isolating organic compounds. People were trying to look at what can be the composition of these organic compounds. The chemistry what has started with carbon, nitrogen, oxygen, is it going further with other atoms? in the molecule. This is something, a very big example. The first, I would say, the entrepreneurship started from here. Perkin was a student of Bayer. The suggestion was that this is quinine. Quinine has a molecular formula C20H24N2O2. By the way, this structure of quinine was not known at that time, only the molecular formula was known. Bayer suggested to Perkin that you take allyl aniline, C10H3N, 2 molecules of this, you heat it with oxygen, you should get quinine. This was the proposal. It might look very ridiculous now, but then those days, you have only those substances. And they think that, okay, you take this and then put oxygen and then heat it, cool it. I must say that some of the schools are doing even now the same. They will boil, cool, filter, take melting point and then be done with that, publish somewhere. I hope there is no printing press in newspaper or somewhere, then publish a paper and say that this is a paper. That's not research. Right? So when they tried doing this, he suggested this, okay, if you heat these 2 molecules and then same molecule, you should get this. He did that. And when he did that, like any other researcher, he also got frustrated because he was getting nothing. And what he got? He got a very nice blue color tar in the flask. Then he thought that, okay, I will wash it out. He put some alcohol and washed it. It spotted everywhere. Then he put a cloth and wiped it off. He realized that the cloth became violet in color. Then blue in color. Then he kept on washing it, but the blue color didn't go off. Then he realized that what he made was some substance which can be a dye, and on any substance, any cloth you put it, it is getting, embedded on top of it, but it is not going out. He realized that I don't need to do a PhD, now I can start an industry. Perkin went back to England, started the so-called mauve, which is there, the fabric which is with that indigo blue. And that is how the dye industry started. Forget about quinine, forget about all the synthesis, he started making indigo. You will be surprised that the Queen of England at that time has given a decree that only she is allowed to use that indigo on the fabric, nobody else, because it is so nice. Okay? This is sometime, 3 years after your college started. Okay? Then people realize that there is some potential for industrial perspective of organic chemistry, you can earn money. So money, knowledge, these 2 things started growing now. So organic chemistry started from something which is synthesis of urea to acetic acid, now it has gone further. When it has gone further, when people were looking at many other things, people started, oh, what is this, what is that, how you can synthesize this, how you can isolate that. The curiosity of organic chemists was, what about the plants, what about the substances, what about the other ones, can we make something out of it? Dye industry means, can we make more dyes, can we make different colors and pigments, everything was there. Then came the synthesis of Willstater. This is back in 1901. We are talking about 124 years before what we are. Now you see something, if you people have observed, urea is a flat molecule, NH2CONH2. Quinine structure is not known, but anilines are known. People started using those aromatic compounds because they are smelling aroma and all that. Richard Willstater got Nobel Prize not for this one but for some other chemistry. He escaped Second World War, moved to Switzerland, and he went there, he didn't come back to Germany. He was much ahead of his time as far as chemistry is concerned. At that time, this compound, propionine, was isolated. Somebody could dare give a structure of a bicyclic compound. We are not even thinking of a cyclic compound. Somebody gave a structure for a bicyclic compound and thought that this should be the structure of propionine. If this is the structure of propionine, can we make it? Now you look at the progression. Organic chemistry is something which can be made only from living objects, has become now a chemistry which can be done from non-living things, and I can make urea. From urea you make aniline, acetic acid, from there anilines, and from there to mauve, indigo and all that. Now you suddenly say that, oh, I want to make a compound which has been isolated. If this is the structure, can you make it in the lab? And Willstater did that synthesis. He started with cycloheptanone. For those who are in MSc, take a look. You have cyclohexanone, you react with hydroxylamine. That means you are making an oxime. When you have a cyclic oxime, always you think of a Beckmann rearrangement. It's not like that. And then you reduce that oxime with sodium and ethanol, means in situ generated hydrogen. You get the amine. Now we react that with methyl iodide, large excess, so that you make the quaternary salt, and then you eliminate it. That is your Hoffman elimination. You get the alkene. When I'm telling you reductive elimination, Hoffman elimination, and all that, these are all the reactions which have been progressed from 1856 to 1901. Almost around 50 years of organic chemistry has seen the Claisen condensation, Hoffman reaction, Beckmann reaction, oximes, and all that. This has progressed. But then, when you have so many methods there, can we put all that to make a substance whose structure you propose something, but can you make it? And this alkene now is reacted with bromine to give you the dibromide, and then you react with dimethylamine. One will do the displacement of the bromine and the other one elimination to give this allylic amine. Now you do the same reaction again, methyl iodide, silver oxide, eliminate it to give the double bond, and then bromine again you brominate and debrominate, you get the heptatriene. And that heptatriene you add HBr, you get protonation of one of these butadienes and reaction with the amine to give you the NMA2, and the other alkene will become the dibromide. And then you heat it, this will make a quaternary salt, and the other bromide will survive. Bicyclic structure. And now you react this with sodium hydroxide, dehydrobromination, followed by silver chloride, and eliminate it, you would get the corresponding amine compound, no quaternization. And then you do the hydration of that alkene with sulfuric acid in presence of HBr, and then oxidize it with chromium trioxide, you get to the ketone. A simple synthesis. At that time, people said that this is one of the most expensive syntheses of this compound. What are the reagents? HBr, H2SO4, hydroxylamine, sodium, ethanol. If this is expensive, then there is something seriously wrong. Why it is very expensive? Because in between you have silver oxide. There are 21 steps, but if you remove the heating and some oxidations and all, totally you have around 15 steps, useful steps. When Willstater did this, perhaps this is the first recorded total synthesis of a product which is isolated in nature, but then the structure is confirmed by synthesis. And I must tell you, by this time, Grignard has reported his Grignard reactions. 1903, 1904 was Grignard. He disclosed his Grignard reactions. And Emil Fischer was proposing his lock and key specificity. People are progressing in a different direction. synthesis was becoming very different. Now when at this stage, this is the tropinin structure and Willstead have published this, Robert Robinson looked at the structure, 1901, this is 1918, and he did this dots, this dot dot dot. Originally in the paper you can see that. And then he wrote in the paper that by the imaginary hydrolysis at the points indicated by the dotted lines, the substance may be resolved into three other fragments, and this observation suggested a line of attack of the problems which has resulted in a direct synthesis. Let's not worry about what has been written there. What Robinson proposed, these, mind you, in those days the terms are not so great. It is not hydrolysis. You don't call it as hydrolysis. But then you put those dotted lines, and then if you see how those dotted lines are dissected, you will find that you have an aldehyde, you have an amine, and you have a keto acid, beta keto acid in presence of calcium carbonate. Heat it, you get the compound in 42% yield. 21 steps, somebody has synthesized, and 17 years later, somebody comes and says you don't require that much. If you put all this, if you mix these three, it should give you the same compound, and he mixed these three and then heated it up. He got this product. That's it. You are sure of a Nobel Prize. This is what we are talking is 1918. He got Nobel Prize in 1947. But for this reaction, nowadays, of course, afterwards you write the mechanisms and all. What the mechanism is, you take succinic acid dialdehyde, you react it with methylamine, so you get to the corresponding iminium ion, and since this is a very acidic beta keto acid, it will add on to this iminium ion. Then you get another iminium ion from the other aldehyde. Then again an intramolecular reaction, you get to the beta keto calcium salt. You know that beta keto acids decarboxylates very fast, so you get tropinin. Now we give the terminology tandem reactions, domino reactions, multi-component reactions. All those examples are here. This is a domino reaction. What is a domino reaction? You take an aldehyde, you make an imine, you react it with a nucleophile, you decarboxylate it at that. Everything in one pot. I don't know what you think about it, but somebody else, if they says that I have done the synthesis in 21 steps, but somebody can look at that and then say that these are the three substances, you mix it, you will get it, and if it goes like that, that would have been really a blockbuster those days. And he could synthesize it in one step, 42% yield. And when Robinson was doing all this synthesis and he was looking at it, there entered Professor Woodward. I don't know how many of you know about Professor Woodward. At the age of 19, he was almost thrown out of MIT for not passing in Latin and in physical education. Those days, those were compulsory subjects. And Professor Falk, Maurice Falk, who was the head of the department, he thought that this boy is very good in chemistry. Let us not insist that he study all the other subjects. He is going to be great. Let us give him a chance to pursue chemistry. At the age of 20, he finished PhD. So, and at the age of 22, he became a professor. At the age of 24, he became a professor at Harvard. And when Woodward thinks about reaction, it works that way. So, there's an enormous understanding, and he was much, much ahead of his time. There was a serious rivalry between Robinson and Woodward. But then the planning and execution of Woodward is beyond comparison, and sometimes it's beyond our imagination. And when he synthesized many compounds. He synthesized quinine, he synthesized reserpine, he synthesized strychnine, he synthesized lysergic acid, he synthesized tetrodotoxin, he synthesized many compounds. But what's very important is that the creativity element is completely different. And in textbooks, I don't know, you might have the synthesis of quinine, but in reserpine, because it has its origin in India, it is isolated from the ashwagandha plant, one of the key medicinal plants. Now look at that structure. They did not have NMR, they did not have anything else. They had only IR, UV and melting point, nothing else. If I give you, I'm sorry to say that some of our institutes still have the same IR, UV, melting point. We did not progress. Now we came, this is in 1956. As I said, from 1901 to 1918 to 1956, the progression from simple urea to that of tropinin, from acetic acid to tropinin to that of reserpine. Now we are talking about stereochemistry, dot bonds, strong bonds. And the concept of stereochemistry is not developed at all. When Wood was looking at his synthesis, he said that, okay, if this is the case, we should be able to make, by the way, there is no term called retrosynthetic analysis at that time. This is for our convenience we are writing now. What Woodward thought that there should be a Diels-Alder reaction between quinone and that of a diene to give you a Decalin type system like this, which can be elaborated to the natural product. I would not go into the details. If MSc students are interested, you look into the synthesis, how Woodward has done the reserpine synthesis and try to see what main reactions are there. You realize that he started with a Diels-Alder reaction between a quinone and that of a diene. You heat it, you would get this compound. And then you reduce one of these ketones selectively without touching the double bonds using Meerwin-Pondorf-Verley reduction. Mind you, this is called chemoselectivity. You don't touch the double bonds. You just touch only the carbonyl group. And then this hydroxy group will react with the ester and give in situ the formation of the lactone. And then what he does? He reacts this with bromine. Now this is a bromo-etherification reaction. That's what you get. From here bromine will form bromonium ion here and this cycloses here to give you that. And then you react it with sodium methoxide. It reacts with this and then elimination of this bromine, beta bromo elimination to give the alpha beta unsaturated lactone, and this OME attacks here to give you the corresponding compound. You can ask me the question, why he has to go this much? Can he not add isomerize here and then add methoxy? Because you need to control the configuration there. When you do the reaction just like that with a bromo or reaction there, it will not give you the stereoselective reaction. There is no term of stereoselectivity, specificity, or stereoselective, stereospecific reactions was not defined at that time. But it was Woodward who thought that there would be some problem if you do just like that, but then you make sure that the stereochemistry of this methoxy would be fixed if you do it in this way. Then he reacts this with N-bromosuccinimide so that electrophilic bromine reacts with nucleophilic alkene and hydroxy will open it up to give you a bromohydrin. And that bromohydrin he reacts with chromic acid or chromate in acetic acid to oxidize this, and then reductive with zinc to open it up to give you the corresponding compound here, which is basically the bromine goes off and this goes out to give you the compound here. And the carboxylic acid reaction with diazomethane gives you the methyl ester. And osmium tetroxide reaction to give you the diol, which is cleaved with periodate or perchloric acid, and then react with diazomethane to give you the ester. Now if I see all this, I might be going pretty fast, but these reactions which are there in 1956, you must have heard of Woodward dihydroxylation, you must have heard about bromoesterification, you must have heard about Bood olefination, or you must have heard about debromohalogenation, or dehydrohalogenation, debromination, dechlorination, dehallucination. These are the same reactions, there is nothing new in this. But then the way he predicted it and then used these simple reactions to come to a very complex structure with exact stereochemistry was something really very nice or unimaginable at that time. And now he reacts this with tryptamine to give the amide. Now what is so great about this? When he did, you people must have known about Bischler-Napelewski synthesis. This is to do with the synthesis of an isoquinoline. Basically, when you react this with POCl3, you will get the enol type structure with Cl here, which the indole would react, and then you reduce the iminium ion with sodium borohydride to give you this structure. Mind you, those days, to check whether you got the same compound or not, I don't know how many of you do practicals in the lab. Whether you are making parabromoaniline, I don't know whether you guys make parabromoaniline, aniline, acetic anhydride, bromination, remove that acetamide, and then you make parabromoaniline. They will ask you to check the melting point. I am sure somebody else will say 100 degrees, you all will write 100 degrees. Nobody has the time to check. But if I ask you, how do you check the purity of your compound? Suppose it has to melt at 100 degrees. Your compound is melting at 90 degrees. What does it indicate? Depression in freezing point, elevation in boiling point. Means there is something wrong with your compound, there is some impurity. How do you know that it is the parabromoaniline? You take the authentic parabromoaniline, check its melting point, you check what you synthesized, you mix these two and then take the melting point again. If they are the same compound, it should have the sharp melting point and the same melting point, whatever it is. If it is not, you will see two different melting points, right? That is the same way when Woodward did the melting point, he realized that this is not melting at the same temperature which the natural product melts. He realized that there is something seriously wrong with the synthesis. But where he can go wrong? If you have to go back and check where he can go wrong, none of these reactions can be wrong because these reactions are Diels-Alder reactions, stereochemistry would be the same. Aluminum isopropoxide you cannot change. And all these reactions, this would be with great stereochemical control. So where it can be wrong? It can be wrong only at this point. Now at this point, if this is a different one, then what is that compound? That can be a diastereomer because rest of the stereogenic centers are same except this stereogenic center. We are talking of diastereomer, enantiomer, apimer. These terminology was not there at Woodward's time. But then he predicted that this is the one which is going to be very, very different and this is the one which is causing it. Then the question is, how do you change it? Now you have several methods to change it. Woodward's time there are no methods. There are only few syntheses are known. And Woodward was a very good fan of Diels-Alder reaction because that was a reaction which was very much known at that time, very much in contention all the way. Then he realized that, look, there is a serious interconversion of these ones. And if something like this happens, he has to do something here to lock the structure. Then he has to see how he can invert the stereochemistry here. We are talking of 1956 chemistry, not 2025. but still it is valid even now. And he realized that if you take indole, I will put it this way, if you take indole, I ask you, where indole is more nucleophilic? Which position of indole is more nucleophilic? It is the third position of indole which is more nucleophilic. If third position of indole is more nucleophilic, if you react that with acid, what happens? The third position of indole will pick the proton and you will get the iminium ion. If you have some substituent here, it can make the enamine. Imine can become enamine. And the enamine, if it picks up the proton again, now it can pick the proton from either side. That means you are trying to epimerize that particular center. Somehow if you can force this epimerization to the way you want, then we can synthesize the compound what he requires. Now we can tell all the analysis. This is like, you know, you watch a cricket match and if somebody hits a century in your home, you watch cricket and then you will say, yeah, hit the shot nicely, this, that way. You can analyze very nicely. But if I ask you to go and play there, you will be the first person to come out without even facing the ball. When you have problem there, Woodward could visualize it and then say that, look, this is the problem, and if you can protonate it that way, indole third position, and you can make the enamine, and the enamine can pick up a proton, then it can be epimeric, and if you can force it to come from the side which you want, then you can make the natural product. How did he do it? He just cleaved this acetate, and this acetate now will become the lactone. Now once it becomes a lactone, it is fixed. Means this conformation is locked. Once it is locked, now you protonate the indole. Now if you protonate the indole, it will go in a position which is like the opposite one which you get. And the acid what you use, it's not like HCl and all you use because it will give you so many mixtures. He took a very bulky acid called tevalic acid. Tertiary carboxylic acid is bulky. There is some kind of a sterics you can exploit there and you get the compound what you want. And once he does that, he simply cleaves it and then he attaches this acid chloride to give reserpine. The reserpine synthesis by Woodward is a great synthesis not because he has done the synthesis. He could change the stereochemistry of a particular center here which is otherwise not found in a Dichter-Napierski reaction, and in the process he defined the reactivity of indole and he defined the reactivity of imine versus enamine. Nowadays in organocatalysis people talk about enamine and imine reactivity. That is something which Woodward did long time back, and they got Nobel Prize also for organocatalysis 2 years back. Woodward predicted it long time back that this would be the stereochemistry of imine versus enamine, and that would be the reactivity of those compounds. In fact, Woodward used a proline catalyzed aldol reaction in one of the synthesis of erythromycin. Okay. When Woodward was doing all, Woodward got Nobel Prize in 1965. Okay? And at that time, the Nobel Committee has mentioned that it looks like that anything that is produced by nature you can produce in lab. Because it was, it's mastery thing of completely different, right? And see, you have however in a spectacular way expanded and enlarged the domain of the possible. This is perhaps a slight exaggeration. What it is sometimes said that you have demonstrated that nothing is impossible in organic synthesis. Then came at that time the synthesis again by E.J. Corey. By the way, E.J. Corey also started at University of Illinois, came to Harvard. Professor Woodward also started at Illinois and came to Harvard. And prostaglandins are very much responsible for plant growth, and those days there was so much of research in prostaglandin synthesis. I'm sure this is there in synthesis is there in your masters. What is something great about Corey is that Robinson did the synthesis by intuition. Yeah, these three, if you mix, you should get propanine, and he got it. It was fantastic. Woodward looked at the reactivity and said, look, if you do this, if you do this, if you do this, you should get it. By the way, Woodward gave the structure of ferrocene. It was not Wilkinson, it was Woodward who suggested to Wilkinson that is the structure of ferrocene. And in fact, when Wilkinson got the Nobel Prize, he was very upset because he gave the structure of ferrocene. And it was Woodward who predicted the Woodward-Hoffman rules. And it was Woodward who predicted the structures of proteins. And it was Woodward who predicted that polymers can be conducting when you have, the polyacetylenes and all. He was much ahead of his time as far as reactivity and this one is concerned, and the prediction of the properties of molecules. But what Corey has proposed is something very different. That is something which everybody can think of. Corey proposed that if you want to do total synthesis of any compound, Corey said that we must identify the target structure. And you say the retrosynthetic analysis, that is something, the word which was introduced by Corey. Means you cut the molecules into smaller fragments and see what is the synthone. That is, synthone means the compound with which you can start with. The two terms of synthone and the retrosynthetic analysis means going back to see what is the starting compound that you can come up with, is something what Corey has suggested. Until that time, people were going with intuition. Nobody has given such a term and then such a very organized analysis of how a synthetic compound should be cut into pieces. And then he said, once you have the selection of the synthone or main building block, you have to look at the availability of that compound. Suppose the availability of those compounds, you can make any crazy retrosynthesis also, but if you think that the starting compound is available at the moon surface, you cannot bring it here. You should look at what is available with you, how you can change and how flexible your synthesis is. All synthesis, if it goes the way you want, then everything goes within 6 months. But then if there is a deadlock or if there is something wrong, then you should have the flexibility to change it. And the flexibility to make analogs also. And then amenability to stereo electronic as well as stereo control. Anybody can make compounds, but if it is a 50-50 mixture or something like that, that's of no use. So you need to see whether you can have the control elements, what I mentioned, chemo, regio, enantio, diastereo, all the controls can you have. And in the case, if it is it known, or it is predictable, or it is desirable, or it is a multi-component, or it is diversity oriented, these questions came up afterwards. Predictable in the sense, if you take aniline and react it with acetic anhydride, you will get acetanilide. There is nothing new in that. But then if you incorporate that into a synthesis and say that if you have 3 amines and one of the amines is very basic and this acetic anhydride would react with that one only, I will get an amide here only, that is something which is a predictive power of a known reaction. So when you have a complex structure and when you dissect it, you need to develop methods. If it is known, then can you think of a method which can be much better than the previous one, or can you think of methods which are completely new but exploiting the reactivity of organic functional groups? And that's what Corey has done. And Corey for the first time introduced something called protecting group chemistry, where you mask the reactivity of one functional group, do the reaction on the other functional group, and once your reaction is over, you remove this protecting group and then bring back the functionality what you want. This is something like masking it for some time. And that protecting group chemistry was something which was introduced by E.J. Corey. Umpolong with Dieter Seebach, he is the one, reversal of polarity. Suppose simple methyl chloride, it's electrophilic or nucleophilic? It is electrophilic. If you want to convert it to a nucleophile, you just add magnesium, it will become Grignard reagent. Once it becomes Grignard reagent, methyl group is negative, that is nucleophilic. You can't call it as Umpolong because you have done the reaction. You cannot regenerate your methyl chloride from Grignard. But then you changed it from electrophile to nucleophile. In the same way, if you have taken a ketone, that carbon can never be negative because it's an electrophilic carbon. But if you want to make it nucleophilic, you react it with 1,3-propane diethol, make it as dithiane, and then you can deprotonate. Then it becomes nucleophilic. That is what is Corey's contribution. You change the polarities, you change the reactivities. At the same time, you mask the reactivity, you mask the functionality. And at the same time, he was the one who started addition of these organocuprates, so-called Gilman cuprates. It was Corey who was used in the synthesis of your prostaglandins. What is this retrosynthesis he has done? This one, whatever you see the dotted lines here, that is Corey's contribution. You might think very different that what is so great about this cutting of these compounds. Until he did it, nobody has ever done that. Nobody has ever thought of a molecule can be dissected. And when he did that, you come to a smaller fragments. These smaller fragments are called the synthones. What you call the synthone. Means from this one you building block, one after the other you construct and you can make the molecule of your kind. What it has given? It has given you the power to think. Even if I give you a molecule now and say dissect it and then make it something reasonable, CC bond forming or C-heteroatom bond forming, you would be able to do that. And even computers do that. If you give it to computer, it can do it. The computer-aided drug design or organic synthesis is there. I mean, you cannot beat a human brain. What computer gives the database, whatever reaction says, it with the new reactivity, it is you who have to propose it. Right? So what Corey has done is that he started with simple compounds that you take cyclopentadiene, react it with dichloroacetyl chloride, you make a ketene here, and then 2+2 cycloaddition of the ketene, and then remove both the chlorines with zinc reductively. You get to this cyclopentane and cyclobutane, a combination of this bicyclic structure. Now you do an oxidative iodolactonization, protect this hydroxy, this is what I am saying, protect this hydroxy, means you mask the reactivity of this hydroxy group. Now you react it with DBU, you remove this iodine, you get the alkene here. This is what you call the corylactone in prostaglandin synthesis. You know, Dr. Ramakrishna Rao mentioned to me that this is being taught in this college for a long time. I don't know whether it's being taught now or not taught or whatever, but this is one of the landmark synthesis of Corey before my birth. Okay? Something which is an extraordinary masterpiece of retrosynthesis. And once you have it, you just have to, you know, this is an acetate, so you do SN2 prime reaction with the copper, 1,4 addition, so you make the addition, and from there simply you do functional group transformations of deprotection of this TBS, cyclization to give the lactone, and from there THP protection of one of the hydroxy groups, diol H reduction of this, you know, lactone to lactal, and a Wittig reaction to give you the prostaglandin, and then you do an oxidation to give the complete prostaglandin synthesis. These are simple reactions. Now by the time you have diol, you have Wittig reaction, you have protection with the THP to DHP to THP, but all the other ones are simple reactions. This is 1960s chemistry. But what Corey taught us? He taught us that you don't need to worry about the structure of the molecule, you can synthesize it by dissecting it to something called synthones, and you should be able to assemble these synthones with reasonable reactions with the reactivity of the functional groups, and where required you can mask the functional group reactivity and regenerate it. Right? So that's what, you know, Corey got the Nobel Prize for organic synthesis in 1990. And in 1990s, early 90s, there is something that has come up very much in organic synthesis. Now we started in 1828. Now we have come up to 1990. Your college 1853. You are at 1990. You got your 1971. When Corey synthesized prostaglandin, you started chemistry courses for PG students. Now we are in 2025, we are still teaching the core synthesis. There should be some transformation, and we should progress further. But then what happened is that something called asymmetric synthesis has come into picture. You know, I was telling Srinivas and Dr. Ramakrishna Rao that it takes another 2-3 classes to give complete lecture on asymmetric synthesis. But I just want to give you, I'm not giving you a lecture on this, but what has come on asymmetric synthesis? How do you do asymmetric synthesis? Olden days of doing before 1970s is that you just do the resolution of racemic compounds. Suppose if it is a basic compound, you know that you put an acid which is available like tartaric acid, malic acid, lactic acid and all, you make a salt and then you separate it, you take out the diastereomer or what you want and then you regenerate the enantiomer and the other one goes waste. The other one is that chiral pool synthesis. Chiral pool synthesis means you start from a compound which is already chiral and then you start doing reactions on that and come to the final product. This is attractive because as much as you have the abundance, then it is pretty good. Mind you, sustainability and organic chemistry doesn't go very well. Yeah, you might say that we pollute a lot by doing reagents and all, but for the progression of the chemistry, sometimes it is required. There are sustainable synthesis also. Now, the other one is chiral auxiliary, means where the reactive functional group is there, you attach this auxiliary, do the reaction, and then remove the auxiliary. But then when you are removing the auxiliary, nothing should happen to the new chiral center what you have generated. If it racemizes or if it does something else, then there is no point. So you have to be very careful what kind of an auxiliary you are attaching. Then comes chiral reagent. Chiral reagent means you have the reagent, it is not catalytic, it is 100% stoichiometric reagent. For example, Brown's IPC2BCl reduction, Brown's allyl boration, bienal H reduction. These are all reagents which are 100% you have to use 1-to-1 reagent. It is not catalytic. Then comes, of course, chiral catalysts and ligands. If you have an amount of chiral catalyst that is 1%, 2%, 3%, can it induce these asymmetric induction in your reaction? Examples are your ketone reductions using oxazoborylidene, ketone reductions using, catalytic amount of hydrogenation reactions also using ligands, biphosphone ligands. Mayori's hydrogenation. These are all catalytic reactions. And then the recent is of organocatalysis, where you don't use a metal, but use an organic compound to do the reaction as a catalyst and then proceed further. Nowadays everybody is coming back to the metal catalyst. Nowadays everybody is coming back to the photocatalyst. Now everybody is trying to do the reactions with photochemistry. That works good to certain compounds, not all. Right? When the concept of asymmetric synthesis has come, you have to develop new reactions for that. And what reactions you developed? Asymmetric reduction, as I said, the Mayori's reduction, the phosphine catalyzed hydrogenation reactions, and then short process asymmetric epoxidation, and then the organocatalysis, as I said, proline catalyzed reactions, and Macmillan catalysts. These four are something I'm sure which is there in your master's book. And of course the sharp process epoxidation with diethyl tartrate and an allylic alcohol, and asymmetric hydrogenation with the BINAP ligand, and of course the asymmetric hydrogenation reductions with CBS reduction and all. Honestly, when I was looking at this, I thought I will have a blackboard also so that I can draw the structures. Okay? But that is anyway something different. I did not prepare the slides for that so that I can impress upon you. I thought I can draw the structures and impress upon you. Anyway, that's different. So once this is done with organocatalysis, now we are progressing towards the synthesis using, the organic photochemistry or photochemistry with catalase or with other reactions. So what is the present day synthesis? Present day synthesis is something like this. Nature makes several molecules. Okay? You know very well that in drug discovery, when you want to make a synthetic compound to a drug, it takes not less than 10 to 12 years. Don't believe in newspapers, they say somebody found a drug and all, nobody will find a drug. It's not that something it is there, you find it and put it. Especially when from natural products, if you are trying to make it phase 1, phase 2, phase 3 clinical trials, it takes a lot of time, effort and money. It's a expensive project. It is not something which is very cheap. And 50% of the marketed drugs you have in the market have their origin to natural products. Okay? So it's important to develop synthetic methods for accessing these natural products. Why? Some of the natural products can be very toxic. Some of the natural products can be very weak. So if you change the structure of the molecule, it might have great effect, and then it can improve the druggable character of your compound. Or sometimes if the toxicity is so high, if you change the molecule, the toxicity can come down and the medicinal importance of the compound can go up. But then if you keep on destructing the environment and keep on cutting, let's say you have a tree which can give you a very good therapeutically important compound, you cannot, cut the tree and start isolating from that. It's important you synthesize it in the laboratory also, so that you can have several compounds for testing their activity. Because these are the natural products which have an unusual activity profile. Sometimes they can inhibit the reactivity of an enzyme, sometimes they can promote the activity of enzymes. And how many natural products you see? You will find many others at the prostaglandins. Allicin is the compound which you have in garlic. And this is, of course, cigotoxin is a marine toxic compound which you will find in sea coast. Taxol, of course, you know very well, which has been used to treat the cancer. But these are all from simple to complex structures. Complexity of the structure also make a lot of difference, right? And in some time you have even, this is the perfume which you use, which smells like jasmine. That is the jasmine. This cis bond is very much important. If it is trans, it doesn't show any smell. It doesn't exhibit any smell. It should be only the cis jasmine. You will be surprised. The biggest industry, chemical industry, is not pharmaceutical industry. It is the perfume and chocolates. The chocolate industry and the perfume industry, it gets more money than your drugs. People are more interested how they look, what scent they are spraying, than what kind of health they have. That is a fact. So we have jasmine, and of course agriculture, this is pyrethroid. AZT is for treating AIDS. And then of course this is phenylethylamine. Basically they call it as falling in love molecule. It is nothing that if you are liking my lecture, this is now produced more in your brain. If you don't like it, maybe it is not there, right? And then of course you have this one, it is hermandicline. This is something which is much more 1,000 times sweeter than sucrose, a sweetener. So when you have this many diverse structures and several other natural products, these are synthetic compounds, but natural products also which are very much having different therapeutic potentials, you have to synthesize it, right? You cannot go and keep on wasting the resources outside. So how do you make it? At the same time, when you look at nature, nature also gives you some kind of a imagination. You don't need to think about natural products only. You can think about non-natural products. You know very well that when you look into the stars, you can make so many, designs on so-called, all what you call, this is something to do with Aries, this is something to do with Gemini, this is something, you can draw several ones. Similar way, when you look at the nature, this is something which, you can draw structures. This is something which is like a dodecahedron type structure. This I took, these slides are not mine, this is the slides of Professor Mehta, who got inspiration from this kind of natural ones to make unnatural products, right? Even making unnatural products is very much important. You need to look at the structure, their stability and their reactivity, how do they behave, this one has to look at, right? So This is, for example, this is fullerene. Fullerene structure, which, can you make fullerene? Can you think about it? If you make carbon-carbon bonds, you can write any kind of carbon-carbon bonds. Look at these structures, for example. This is 660 fullerene. This is a bowl-like structure, which is these atoms are sulfur. And these are octanitrocubane. And these are something, a ladderane, this is cyclobutane. But these are something like triangulene, these are cyclopropane rings. These are something which I am giving an example. Tomorrow if you draw a rangoli and then it is a carbon-carbon bond if you think, but can you make it in lab? If you want to make it in lab, how do you make it? Can you think of a reaction? And if it is so simple molecule, is it energetically stable? Can you see it? How can you characterize it? And if it is something which is characterizable, what can be the property if I heat it? Or if I do the reaction with, does cyclopropane sit like that, or will it open, or some other reactions will be formed? If it is so, does it release energy? If it releases energy, can I use it as a substitute for something? Or if it abstracts energy, can I use it for substitute for something? What kind of a detection I will use? What kind of a spectroscopic techniques I will use? Does it exhibit different color? If I shine light, does the color become from red to blue, blue to something? So when you look at materials or when you look at the physical chemistry of organic compounds, this is what something people look at. If you excite it, does it come from the ground state to the excited state, and if it is coming back to the ground state, does it, emit something, the light which emits, can you use it for something else? These are some physical properties which you are looking at. So organic chemistry, what happened now? Not just natural product synthesis or synthetic methods or something like that. It has gone into the allied fields. As you know, okay. It has gone into the allied fields. Means in materials you require, in bioimaging you require, in MRI you require. In short term, if I have to say that it requires in human well-being, it requires in your health, it requires in your sophistication. Suppose the displays what you have, these are all, some of them are organic materials, of course. And it requires in your understanding of the reactivity of your functional groups and imagination of this type of compounds. And some of these are chiral, by the way. If you put a linear one or you put up and down, you know that there are something which can be chiral also, if you have substituents on top of it. How do we make it? This was the question which Professor Mehta asked himself, and then some of these compounds are made in his lab. And some of the crystal structures were taken. That was in the University of Hyderabad. I must tell you that Ramakrishna Rao worked with him in 1979. He was our director at IASC until 2005. He is now a national research professor at the University of Hyderabad. He was one of those giants in organic synthesis in this country who taught us to daringly ask for the solutions for doing organic synthesis. Okay. Now, you can think of those molecules also. I picked up from the book, if at all you have this, you can, old book called Organic Chemistry, The Main Game. Okay. From that book you can find out several different funny compounds, funny structures and all that. You write a structure like that, it is very nicely written and all, but if I ask you, go to lab and synthesize it, how does it look like? Just cut it, cut this one, cut this one, cut this one, cut this one. I took the book from, old Cram and Hammond book has all these ones, open it up, you will see all kinds of crazy structures. You write it cyclopropane, cyclopropane, cyclobutane, cyclobutane. Some of them can be made, some of them cannot be made. Synthetic organic chemistry doesn't restrict itself to the natural product synthesis. But natural product synthesis gives you a window to explore into further allied areas. Okay? So this is something which, as I said, to give you a thought like what kind of structures one can think of or what kind of structures one can make. Okay? So when you are trying to do synthesis, when it should be called as a good synthesis, it should be starting from readily available materials. It should be brief. Like what we have seen Willstatter synthesis, at that time it might be longer, but it should be brief. And of course use efficient and selective reactions, avoid extreme unsafe reagents, be flexible, be adaptable. In medicinal chemistry, you have to make several compounds. So you have to be very adaptable for discovery chemistry, and more importantly sustainable. So it should be green and cost effective process, because let's say there is something called high volume low income reactions. Paracetamol, if you synthesize, how best method you have, Dolo cannot be sold for 1000 rupees. Dolo can be sold only for 100 rupees. So even if you have a great method, the pharmaceutical industry will tell, can you make it in 5 rupees? These are called high volume low income products. But if you want to make Taxol, Taxol is very effective at 10 milligram scale. So if you make 100 milligram, you will get 10 lakh rupees. But you have to make 100 milligram, that is low volume, high income reactions, high income compounds. But at the same time, you should be green and cost effective. And of course, you don't want to reproduce the reactions of 1920s and 40s now. You have to think, you have to be innovative, you have to be elegant, and even it has to be artistic. Sometimes, I would say, you might require 1 or 2 item songs to make the movie to run, right? Sometimes, but if that is more, your chemistry would not go. It requires little bit art, science, logic, and execution. That is what it is. You have to be innovative, elegant, and even artistic. I don't know how much time do I have. Can I take another 5 minutes? Okay. So, after all this, you can ask me the question, sir, you have given me the history of organic chemistry and all that, enough jnana to us, but what is that you do at IISc, right? We do at IISc, we do the synthesis. Of course, before I go into the synthesis of our synthesis, I just want to give this synthesis by Phil Barron. He came in October, he came to IICT to give a talk. He is one of the best synthetic chemists nowadays in organic chemistry field. He works at Scripps Research Institute. He synthesized this compound called ambiguine H. He was a student of K.C. Mikalau, postdoc with E.J. Corey. E.J. Corey did protecting group synthesis. He did protecting group free synthesis of one of these compounds. How he did it? He started with this is a hydroboration of limonene. You do it, you get this compound. And then you do a cyclopropanation using trichloroacetyl chloride and zinc. This is basically the ketene addition followed by sodium methoxide, you get it. And then dival H to reduce that, and then make a elimination to give this alkene. And then you have sodium iodide, you remove this mesityle to the Finkelstein reaction, and then elimination to give the alkene. And this is a new reaction. This is called Buchwald-Hartwig coupling of this alpha halogenate, alpha arylation of a ketone using copper and lithium HMDS as a base. And then he put palladium reaction to do a Heck type reaction here, and then reductive amination to give this isocyanate. Few step synthesis without protecting groups, using protecting groups. So this is something you would not require it. This is basically to say that he has made the core structure using the protecting group free synthesis of this compound. When we were looking at IISc when I joined, I'm sorry about this slide because this should be in PowerPoint presentation. There is something wrong with what I got. My computer is a Mac computer, so I could not connect it there. So I made it into a PDF file, so sometimes it won't show that. Okay, I'm sorry about it. So when we looked into the synthesis of some of these polyol structures, so many hydroxy groups which you find in carbohydrates, we thought that can we make it from readily available compounds? And that readily available compound, what we thought was, if you make from tartaric acid this amide, amides, when you add Grignard reagents, the first step would be formation of a ketone, and then if you add excess reagent, it will become a tertiary alcohol. But can we stop it at a ketone stage? And this is a C2 symmetric compound. If you add one equivalent, can you stop it at one ketone stage and leave the other amide? If you can do that, then what happens, you can reduce the ketone to the hydroxy, then add the second Grignard and then do second reduction. Now you open it up, you will have so many hydroxy groups in the system. And this depending on what kind of grignard you use, you can make several of these building blocks. Like you can make aryl, alkyl, alkynyl, vinyl, all that you can make. And once you make it, you use this as a start point for the synthesis of natural products. And what natural products we made, I'll just take it. These are some of the natural products which we synthesized in our laboratory using tartaric acid as the start point. This is called a chiral pool synthesis, where you start from a chiral compound which is abundantly available, and then you do reactions which are stereoselective with minimal amount of purifications in diastereoselective reactions. Most of the reactions would be diastereoselective, and then you progress with that to make all these natural products something which is simple to that of a very complex systems. These are called macrolactone systems. That is what we do in IAC. Okay, something to do with the natural product synthesis using chiral pool compounds. So that is where I end. I hope I have given you some introduction of the history of organic chemistry, tried to connect you from where Wohler was and where the current state of the art, and how we are progressing very rapidly into the several dimensions of organic chemistry and its effect in allied fields. So if at all you have something, if you have to come that side, this is how our institute looks like. Some of you must have visited. This is one of the beautiful campuses in the country, very nice flowering campus all the time, sometime you see. So our institute started by the endowment of J.N. Tata, not as old as Zohar College. We started in 1909, and then we are now like the time when Will Stater synthesized it, and we are now progressing further. Okay? So thank you very much for your invitation, and I will be happy to answer any questions you have. Thank
Dear students, if you have any questions, please.
Great. Okay. Thank you. Thank you so much. Please take that from them.
Any questions from participants, business scholars, students?
If you don't have questions, means either you did not understand completely or you understood 100%. Yeah, especially the students. Anyway, that's fine.
So, if you have no questions, it is time to propose vote of thanks for this session. So, on behalf of the Department of Chemistry and student community, so thank you sir, thank you so much for giving a wonderful talk on progression of organic synthesis from Wohler to the current status. So SAR started all the history of the organic chemistry, where it started from Wohler and covered many renowned scientists in organic chemistry who contributed a lot to the organic synthesis. That is Wohler, Perkin and E.J. Korigaru, Wohler. At that time, how they worked, how they imagined, and like each and every point with history SAR explained in detail. So thank you sir, thank you so much. I hope all the students enjoyed the history of organic chemistry. So now we'll take the lunch break, afternoon at 1:30.
Good afternoon to one and all. So I request all the faculty members, students, so please assemble at the seminar hall. So we'll have an afternoon sessions. Once again, it's a gentle reminder to all the faculty members. So now we have a technical session in the afternoon session. So today's session, afternoon session is being chaired by Dr. Surya Garu. So we'll have a talk from the resource person, Dr. D. Adinarayan Garu from SERB, Barampur, Orissa State. So we'll have a talk on stereo electronically tuned NSC supported species, its versatile platforms in metal free and metal based homogeneous catalysis. So at this juncture, now I invite Dr. Surya Garu from the Department of Chemistry. So to give a brief profile about this great eminent scientist, please madam.
Thank you, sir. Good afternoon to all. Welcome back to the post-lunch sessions. Now, I take the privilege of introducing our next speaker, Dr. Adinarayana Garu D. Dr. Adinarayana is an eminent associate professor in the Department of Chemical Sciences at Indian Institute of Science, Education and Research, IISER, Barampur, Odisha. He is specialized in main group and organometallic chemistry with research interests spanning sustainable homogeneous catalysis, ligand design, metal-metal bonded species, and frustrated Lewis pair chemistry. Dr. Adinarayana completed his PhD in synthetic organometallic and nanomaterial chemistry at Ruhr University, Germany, focusing on low-valent gallium-supported organometallic compounds and nickel-gallium nanoparticles, and holds his MSc degree from IIT Madras and qualified all levels of entrance examinations like GATE, JAM, etc. He has held many academic and research positions in Germany as well as India, including the postdoc work at Technical University, Braunschweig, and held his multiple faculty roles at IISER, Barampur. His accomplishments include numerous peer-reviewed publications, book chapters, invited talks, and externally funded research projects. He also gained several prestigious projects including Ramanujan Fellowship Grant from Government of India. With expertise in both teaching and research supervision, Dr. Adinarayana continues to contribute to the advancement of inorganic and organometallic chemistry while playing an active role in organizing national and international scientific events. Now, I welcome Dr. Adinarayana Todi to give his lecture. Thank you, everyone.
Are you using this one? You don't have mic?
Thank you, sir.
Is it okay? I'll put it here. Okay. Okay. So I'm audible enough. I hope there is a full clarity in voice, right? It's not too loud or too low. Okay? Yeah, okay. So, first of all, good evening, good afternoon all of you. And out of my context, I would like to thank the organizers of IC Rise for kindly inviting us to this great college, which has excellent, history and great people from this place. I did my BSc from AML College, Anakapalli, you might already know. So I remember how I had my days during my BSc. In AML College, like you can see the railway track just goes beside that college. Okay, outside that, very nice to be here. So I would like to use the next few minutes with the following title. I would like to bring out main group metal chemistry, like metal-free catalysis, metal-based catalysis, especially in the carbon dioxide conversion reactions. So since I know all your backgrounds like BSc and MSc, and so I would like try to be as fundamental as possible, rather concentrating on like most advanced research. So let me try whether I will be able to convince in the next few minutes of my talk. As the chairperson nicely pointed out, you will see in the next few minutes lots of anhydrous cyclic carbene chemistry, their complexes of main group compounds as well as transition metals, and their utility in homogeneous catalysis. So let me quickly advertise my group. So we work on a main group organometallics and transition metal organometallic chemistry, with the main aim of their utility or applications in homogeneous catalysis. Especially our work starts from ligand design. By designing new ligands, you can achieve particular like characteristic compounds. Actually, you can have like catalytic activity of such compounds. You can achieve from the ligand design actually. So we don't use metal salts. We use molecular organometallic compounds and study their reactivity, utility in especially bond activation reactions as well as small molecules such as carbon dioxide. So we see our work always in this area: small molecule activation, metal-free catalysis. We try to avoid sometimes metal-free. Of course, we do a lot of basic research, and we also look for cooperative catalysis. Two metals, two transition metals, or main group metal or transition metal, how do they interact to give some interesting compounds? That's also one of the part of my group's work. And aqueous organometallic chemistry. And you all know many organometallic compounds are highly sensitive to moisture, air, and dry solvents, right? For example, water or oxygen. They immediately decompose to some useless compounds. So, but can we make an organometallic compound which is stable to moisture and oxygen so that you have least loss of those compounds? So we develop such compounds from the ligand design. So we make a ligand in such a way that the corresponding transition metal complex is soluble in water. So why water is important? Green solvent. We can do a lot of catalytic reactions in water molecule, in water as the solvent. Number one. Number two, many of such compounds can have biological relevance, because biological relevant compounds needs a minimum thing that small amount of complex or metal complex should be soluble in water. That is useful for biological sciences. So we also collaborated some of our complexes with those biology research works. So with that, let me quickly show you the kind of overall work we are doing at ISA Dharampur. You can see we work on anhydrous cyclic carbene supported copper complexes and their utility in the complex organic synthesis. So these kind of compounds, as a catalyst, as I said, we do a lot of catalysis. Using this catalyst, you can make such a molecule into highly fused systems actually in a one-part synthesis. And then, as I said, for example, one of my students sitting here, Maqsood, also works on this class of compounds where we put the carbene and to a bipyridine ligand so that kind of systems can allow us to bring two metals, whether that can be both main group metal or one main group metal, one transition metal. So I hope you know what are the main group metals. S block metal, P block metals, right? These are main group metals: lithium, sodium, potassium, gallium, aluminium, indium, thallium. So all these are main group metals, right? Transition metals, 3D, 4D, 5D. So mostly we try to avoid these expensive metals such as 4D and 5D, ruthenium, iridium, platinum, palladium. So these are super expensive metals. Our group also works, we avoid transition metals which are expensive but show the same catalytic reactions without metal or cheaper metals such as cobalt, iron, nickel, right? Manganese, all of them. So there is one class of compounds. Another one is that you can see the ligands like pyridine anchored sulfur nitrogen ligands. These kind of compounds are very cool ligands. They can stabilize transition metal cations in solution actually. That's the beauty of this kind of compounds. And second class of compounds we have been working on, you can see this ortho-substituted silyl phosphenes. These kind of compounds can also be cool ligands because the phosphorus center, the moment phosphorus center stabilizes the metal center, the silicon main group metal is close proximity to the metal, and it can also interact with the transition metal to give you some interesting compounds like Ragesh is working on this particular area. As I said, this is an extension of this ligand. You can see these ligands also facilitate us to make clusters. For example, the same ligand with copper will give you monometallic complex. Only one metal you can stabilize. But if you go to the silver, gold, it gives you trimetallic, tetrametallic like clusters actually. And those clusters we use, exploit them. We don't just make the compounds and publish. We see their synthesis, utility in homogeneous catalysis. For example, this class of compounds are highly useful in supramolecular catalysis. For example, the silver cluster is a useful catalyst to achieve some interesting organic compounds which are biologically active. So just recently one of our paper also got accepted. You can see that it's a main group hydrates. Maybe your teachers are teaching you. What are the main group hydrates? You know what are the main group hydrates? MSc students? Do you know any main group hydrate? Is ammonia a main group hydrate compound? A lithium hydrate? Silicon H. CH is methane main group hydrate compound. Right? So silicon H, aluminum H, lithium H, sodium H, like calcium hydrate, these are main group hydrates. These hydrates are highly reactive to moisture and air. So similarly silicon H, once you have the silicon H, it doesn't keep quiet. And we exploit that reactivity. When we bring transition metals, it interacts with palladium silicon bonds and give you very fundamental interesting compounds. You all know, right? 3D to 4D to 5D, what happens? Do they give more tetrahedrally coordinated complexes or square planar complexes? When you taught 3D to 4D, 4D to 5D, when you reach down, they always tend to form more square planar complexes rather tetrahedrally coordinated. It's because of the higher crystal field stabilization energy, right? Nickel NaCl4 minus is tetrahedral, but platinum tetrachloride, palladium tetrachloride, those are square planar, right? Same group metals, same oxidation state, same ligands attached to the transition metal, but they tend to show different like geometries because of the crystal field stabilization energies. CFT, I hope your teachers might have already taught. So like this, we have been exploiting this chemistry and see their applications. So let me start today. This particular area, we all know triphenylphosphine. Have you seen triphenylphosphine in your UG/PG laboratories? It's a very simple white solid, right? It is not really so reactive, but also it's quite reactive also. Over a period of time, it becomes phosphine oxide, right? Phosphine oxide, phosphorus 5, which is not really useful. But triphenylphosphine is low valent compound, is phosphorus 3, which carries a lone pair of electron. These are interesting ligands in organometallic chemistry. For example, Wilkinson's catalyst, as you know, is a great hydrogenation catalyst, right? So if you start from triphenylphosphine, you knock off one of the R group, then you get a cationic, because you are knocking off one R group, right? It's cationic. And this kind of compounds are highly reactive, elusive species in the solid state. So you cannot isolate them like triphenylphosphine oxide, which is there in the laboratory. So you need to stabilize such kind of compounds using ligands such as carbenes, anorthoscyclic olefins or amines. So why you need to stabilize them? It's a cool ligands. You can develop some new chemistry, of course, maybe fundamentally more interesting chemistry, for instance. So you can use their ligands, use such ligands to isolate main group metal complexes or transition metal complexes, and they do exhibit different electronics and sterics. I'll tell you what are those different electronics and sterics. As you can see here, if you take some sort of chlorophosphine, get rid of one of the chloride by reacting with anorthoscyclic carbene, they become cationic phosphines. It's no more like triphenylphosphine, right? You brought the cationic charge, and let's say you use anorthoscyclic olefin, it's NHO, right? These are called NHO ligands, right? You can also like make new NHOP phosphines. These are anorthoscyclic olefin phosphines. If you have that kind of compound, these are not only good sigma donors, but also good pi acceptors. You know your textbook chemistry, you go to textbook chemistry, sigma donors, pi acceptors. Why pi acceptors? Some of the compounds are pi acceptors. It's because of the NT-PG orbitals, right? They accept the electrons from transition metal, so thereby it tune the metals electronics either more electron rich or more electron poor. For example, this kind of compounds makes metals electron poor if you attach, because they are good sigma donors. At the same time, they also accept electrons in the phosphorus center, is because of the cationic charge, right? They have anti-pi star antibonding molecule. Because you all know sigma, pi star, sigma star, right? So homolumo gas, you know all these reactions occurs at homolumo, right? If you make homolumo gap smaller, those compounds are more reactive. So that's exactly we all do switch activation, bond activations of dihydrogen, carbon dioxide, carbon monoxide. So we exploit the ligands electronics by making homo-lumo gaps smaller and smaller and smaller. So thereby reactivity increases. So this is what this class of compounds does in fundamental point of view. So why we need to make metal center electron poor? If metal is becoming electron poor, it tends to become more Lewis acidic. If metal center is more Lewis acidic, that kind of acidic metals can activate alkynes easily because alkynes are pi donors. So that's the concept of this sort of ligands. So what is this anerocyclic olefin? These are simple olefins, but a carbene is attached to that kind of olefins. These are called zwitterionic species because the positive charge can be nicely stabilized by this imidazole ring, and the negative charge can sit on the terminally coordinated carbon center. So that kind of species can also be like carbene supported carbenes, right? Anerocyclic carbene supported another carbene, like a carbene, right? And these are very cool ligands. And because when the lone pair is there, they can act as like a phosphine, like a simple sigma donors, actually. Okay? We can also get rid of one of the hydrogen center, and they become NHOPs. There's NHO, there's anionic NHOs, right? So they can act as now sigma donors as well as pi donor. This is the electronics at the fundamental level of this kind of compounds. So we exploit their reactivity to isolate novel organometallic compounds or main group complexes by using this class of ligands reactivity. So for example, you see that we have used this chloro-diphenyl phosphine. If you get rid of this chloride by attaching anerocyclic olefin, the phosphorus center gives you minus 14.0 ppm. So you may not understand at this level, higher the negative charge, right? Higher the negative value, they are more electron rich, right? So you can see chloro-diphenyl phosphine gives 81 ppm, but the moment you throw an HOP on the phosphorus center, they becomes minus 14 ppm, which means that the phosphorus now becomes more electron rich, right? Diphenyl phosphine minus 6 ppm. The moment you decorate this phosphorus center with other ligands, other groups, they tend to become more electron rich. So if they are electron rich, they are more reactive, you can exploit their reactivity. So that's where we put our mind, we spend our time on that one. Okay, then what we did, how we prepare these compounds, of course this complex synthesis in the laboratory, you have to attach this anerocyclic olefin at the phosphorus center. We have created these anerocyclic olefins in situ, these highly reactive species, then treated this compound with chloro-diphenyl phosphine, and that way we can prepare these cationic phosphines. So similarly, we have brought, these are called benzimidazole as well as imidazole. But you see that if you bring more and more aromatics in any compound, you all know they become more stable, right? Benzene to naphthalene, naphthalene to anthracene, because you have more aromaticity in the molecule, they tend to become more stable, they bring more stability. So similarly, for example, the 1 and 2 compounds, compound 2 is more stable, compound 2. So it allows us to work with that compound and develop some new chemistry, for instance, right? So you can see the phosphorus NMRs that you may, I hope you try to understand that. The free phosphines resonates at low chemical strength values, but the moment you put carbenes, they tend to become very lower. So by tuning these electronics, we can make them electron-rich phosphines. So like this, you can see we have made a series of phosphine compounds, and we have exploited their reactivity by preparing this sulfur compounds, selenium compounds, and etc. So we are using synthetic main group chemistry aspects. You can also see that these cationic phosphines can be nicely converted into the neutral phosphines. For example, this is phosphorus 5, phosphorus 3, cationic. You can treat with any base. For example, triethylamine in the laboratory is there, beta lithium, or COB, or sodium hydride. You can use this kind of basis. You can convert these compounds, cationic ones, into the neutral. Once they become neutral, they are highly soluble. You can use non-polar solvents. What are the non-polar solvents? Hexane, benzene, toluene, and etc. These compounds are soluble in non-polar solvents, so that allows you to do something interesting chemistry. Right? Yeah. And these are the single crystal X-ray structures. It's a photograph of the molecule. There is an X-ray instrument. You might already have this one. So you can see what are the bonds, how the atoms are connected in the solid state, right? You can see the phosphorus center is nicely tetrahedrally coordinated phosphorus center, so that can be elucidated by single crystal X-ray diffraction method. That is, we widely use it for understanding the molecules. Okay, we wanted to see, phosphines are Lewis acids or Lewis bases. Huh? Phosphines are loose acids or loose bases? MSc student. Loose acid, loose base. So phosphine is loose acid or base? Yeah, loose base, right? So it gives electrons to any other foreign moiety. Is supposed to be loose acid, right? That's very nice. Very good. Nice. So we try to see whether this phosphine center has lone pair. Can we exploit the reactivity towards acids? For example, boron. Boron compounds are highly loose acidic, right? BCl3, BF3, right? These ones. So if you treat this compound with BH3 adductor, which is tebular, it forms a like loose acid base adduct. Phosphorus is loose donor, boron is loose acid. So we use simple textbook concepts to prepare the compounds of interest. Actually, they are very interesting compounds, but the concept is simply textbook chemistry. Your +2 level, BSc level, MSc level concepts. So there is the molecular structure. Again, you can see it's a main group hydrate. For example, boron hydrates are main group hydrates, right? It's a main group hydrate, loose acid base adduct. Okay, we made it like this. So, but as I said previously, our main aim is to employ these compounds in carbon dioxide utilization reactions. You know, carbon dioxide is one of the greenhouse gases. You all know, right? And you see every day in paper, newspaper, and etc. is a global warming. Why carbon dioxide is the most culprit for global warming? How many of you know, students? Why not dinitrogen? You have a lot of dinitrogen here, right? Then oxygen is there, dinitrogen is there. Everything is going in our body. CO2 is also. Why CO2 is creating global warming? You all know? So carbon dioxide has the ability to store energy, right? It stores energy. So that heat actually, that heat. So wherever more CO2 is there you will see a lot of heat. Let's say here we stop all the fans and ACs. After half an hour, 1 hour, we will be exhausted. You will see a lot of heat generated because we generate a lot of CO2. So CO2 doesn't allow the heat to go away. It stores the heat. So that's what we should get rid of CO2, right? The global warming is because of CO2. CO2 generates heat, right? Stores the heat, right? Then automatically global warming is happening. So at some point, as per the news, at some point people say that Mumbai may not be there. Mumbai will be underwater actually. It's like Mathura and other people, right? So it's because of the global warming. So there is big concepts. We also try to exploit little bit from laboratory scale. Can we convert CO2 into useful compounds by CO2 reduction or CO2 hydrosilylation, conversion, all this using simple concepts. So, but of course, this is too much for you, for your level. These are called FLPs, frustrated loose acid base pairs. People have used this concept to stabilize or trap carbon dioxide into loose base as well as loose acid. So this is a nice concept utilized so that CO2 can be trapped between these two acid and base poles, right? And of course, a lot of people do. David Milstein from Germany and Douglas Stefan from Canada. These people are pioneers in this work. They have developed excellent work on CO2 trapping and utilization into some other compounds. But how we connect, our group is connected to this. For example, phosphines, you can see, typical triphenyl phosphine doesn't react with CO2, right? Or carbon disulfide, these are linear molecules. But these kind of phosphines, which are now electronically tuned, they are different than triphenyl phosphine. So they react with CO2, carbon dioxide, and give the corresponding carboxylate adducts. So such kind of compounds were reported in high impact journals like JACS, Sanghavante, and Nature's actually. So in a similar aspect, for example, you can see that triphenyl phosphine doesn't react with carbon dioxide or carbon disulfide, we check in our laboratory. But the phosphine we have developed, it is super reactive with carbon dioxide or carbon disulfide. Within 10 minutes, you see it traps CO2 gas into the molecule. For example, you can see it can be carbon disulfide or carbon dioxide. Within 10 minutes, you see dark orange solid forms out of the solution, and you can see it happens double activation. One CO2 sits on the phosphorus center, other CO2 inserts between the PC bond. It's a very interesting compound, very interesting observation that we observed, but of course, we were not expecting. It's simply, accidental actually. Then we are trying to understand how we can prepare this compound. So then what happens, this compound, under high vacuum, you have vacuum pumps in your laboratory. If you put under high vacuum, one of the CO2 sucks out. So you have only one CO2 which is inserted between PC bond, which means that the PCO2 bond is highly fragile. Under high vacuums, you can get rid of one CO2, which means that phosphine doesn't form stable complexes with carbon dioxide or carbon disulfides. Right? For example, I see my student actually, let me show you here. You see here, it's a clear solution, right? After some time, there is a video actually. You see this one, yeah, you see that it's starting red, it becomes dark orange. The moment you add CO2 or CS2, it immediately traps CO2 to give the corresponding thiocarboxylate adducts, and that can also seen by some spectroscopic details. So then what we have used these compounds as catalysts, CO2 conversion or CS2 conversion into insertion of the, for example, you can see these are epoxides. You have the epoxides, right? So you treat this epoxide with this catalyst, either cationic one or neutral one, they insert into the cyclopropanes, epoxides to give the corresponding carbo-dithiolates actually. You can see these dithiocarbonates. These thiocarbonates, dithiocarbonates are really useful in industry, in polymer chemistry actually. So people want this kind of compounds in pure form so that people can make polycarbonates. And these are industrially relevant compounds. So such kind of compounds can be easily prepared without metals. You don't need any transition metal, very expensive metal. We're simply using main group compound, we can prepare that kind of cyclic carbonates. So of course, how we always try to make synthesis easy. You make those compounds, column chromatography, you take column, just pass the compound, you can nicely separate the compounds easily. So it makes easy synthesis, workup is so easy, and metal free, you are not adding any metal here, and additives free, people add additives so that reaction goes faster. So you don't need any of that compound and doesn't need harsh conditions. It's very simple, room temperature. Within 90 minutes you get these compounds in good use. You can see this is the substrate scope. Lots of such compounds were synthesized and completely characterized. And most importantly, carbon dioxide. That was carbon disulfide, and carbon dioxide also you can see. We use simply balloon. You don't need pressure. Simply we have balloons where kids play the balloon. You take the balloon, put CO2 gas and tight it and attach to the slung tube or reaction vessel so that it got exposed to the CO2 and then it does the reaction. Now CO2, this phosphorescent takes the CO2 gas and give the corresponding carbonates. So these were also prepared and completely characterized. Okay, that is one set. What about the amines? Can we convert amines to the corresponding amides, N-formulation? N-formulated compounds are very useful in the drug industry actually. That kind of compounds are very useful. Can you convert amines to the corresponding formulation product from CO2? Because CO2 earth abundant, lot of CO2 is there, useless CO2 around us, and is useless, nobody wants, but convert into something useful, right? So we use CO2 gas balloon and treat this with different amines. You can get the corresponding one formulation products simply using balloons actually. So you can see we have screened lots of amines. Whatever the amine you bring, primary amine, secondary amine, we can able to convert them into the corresponding one formulation products. In synthetic organic chemistry perspective, for example, amides, converting amides into the one formulation products is challenging. We need multiple synthetic methods, synthetic protocol we have to use to convert them. But this kind of protocol, you don't need any metal. You just need CO2 balloon, you can convert them to corresponding NH right into the one formulation product. So we are now trying to increase this substrate scope more and more. So like this. And of course, this is a little bit high level theory, you may not be able to understand that. So I will cut short this one, maybe by telling one thing. You can see, just don't worry about the number, just look at the graph. You can see triphenyl phosphine reacts with CO2 and forms a loosely bound phosphorus CO2 adduct, right? Then forms a typical adduct. You can see the intermediate and the compound has almost same energy, which means that it's not giving thermodynamically stable phosphine CO2 adduct. That is why there is no reaction with fast fuel with CO2. So that can be nicely corroborated with DFT calculations. Why triphenyl phosphine is not reacting with CO2 or CS2 is because the intermediate has similar energy than the product. Product should always have lower energy, right? Then you can isolate. Low energy, high stability. So that doesn't happen in case of triphenyl phosphine. Right, and then of course a lot of theory that you may be difficult to understand that, I will cut short it. So then we have utilized this carbon dioxide as a C1 carbon source, right? It's, you always say atom economy, right? You use only one molecule of carbon in the reactants. Can you convert that whole molecule, atoms, 100% into the product? So these are exactly atom economic procedures by using metal-free approaches. So you can see, for example, here, and when you do any reaction, you need to understand, you need to establish mechanism, how it has happened. So we do a lot of reactions to establish this, what is happening. We do a lot of DFT, spectroscopic methods, proton, carbon, mass, right, all these IR spectroscopy to establish, to understand this what happening. That's why we are getting this kind of compound. So we do a lot of work in that perspective. So we do, you can see that when you do this amine with silane without catalyst, no reaction. Right, which means that you need to have the catalyst. So we need to have that catalyst, otherwise this reaction, this conversion doesn't occur. Number one. Number two, you all know, right, your teachers might have taught you homogeneous catalysis and heterogeneous catalysis. Right? We need to find out whether this catalytic system follows homogeneous pathway or heterogeneous pathway. So we need to use amalgam. You know, mercury is very poisonous, I know that. In India, of course, we follow, but many foreign countries, they don't follow. But India we follow because of we do different chemistry. So mercury we use a lot of mercury to understand your reaction is a homogeneous reaction or heterogeneous reaction. For example, Fischer-Haber process synthesis is there, right? Ammonia synthesis. Is it homogeneous or heterogeneous method? How many of you know? Ammonia synthesis by Fischer-Haber. Homogeneous reaction or heterogeneous? It's not homogeneous, it's heterogeneous. It's typically dihydrogen N2, right? It is surface chemistry. In surface chemistry, it's purely heterogeneous reaction, right? So we need to find out whether our reactions are homogeneous or heterogeneous. And what we do, we just throw mercury. Mercury has a property to make amalgams. If you take gold, you buy fresh gold from a jewelry shop and make mercury and mix them, you will not see gold. Because mercury dissolve gold to give you amalgam, actually. It is liquid, right? Mercury is liquid. So then what happens, if you have any nanoparticles, or if you have a catalyst, any nanoparticles which are heterogeneous, right? Once the moment you add mercury, all the nanoparticles will combine with mercury and give some amalgam. The moment all nanoparticles are converted into amalgam, then you will not see any catalytic reaction, right? Because all the nanoparticles are converted into amalgam. The moment they are becoming amalgam, you won't see any products. So like this, we determine whether the proposed reaction is homogeneous or heterogeneous. So when you treat those compounds with mercury, for example, here, well, I'm not showing here, for example. So we add mercury and see that this is homogeneous reaction because there is no change. You will get same yields, same procedure. Means that there are no nanoparticles in the reaction that may be causing heterogeneous method. So we need to find out that is not heterogeneous but rather homogeneous. So we do like that kind of reactions. And also in this kind of reactions, N formulation occurs through, this is so-called silyl formates. You can see silyl formates. These are not easy to isolate in the laboratory, any high synthetic laboratory. These are only highly elusive species. They form in situ, they immediately convert into the product. So how do you know these silyl formates are forming in the solution? So we use a lot of spectroscopic methods such as proton NMR, carbon-13 NMR. I hope you have some idea. For example, you can see this silane reacts with CO2 in place of catalyst with the silyl derivative, silyl formate. That you can see from GCMS and proton and carbon-13 NMR. So they are in situ, these silyl formates are forming. These are the responsible thing to give the products. So we did a lot of reactions to establish that one. So then what we have done, this is the mechanism, the metal-free catalyst first reacts with Ce2 to give us a doubly insertion product, and then that reacts with epoxide and opens the ring actually, and gives you the corresponding alkoxide derivative. This alkoxide derivative now rearranges to give the cyclic product by regenerating the catalyst to the reaction mixture. So this is the mechanism actually. And we did, my students, Amir did lot of reactions to understand the mechanism. You can see all these ones like in situ. Some reactions, something happened, we don't know. You cannot see with your eyes, you only see the colors. So you need to isolate this compound and immediately see the spectroscopic methods and assign them for understanding. So we try to assign those compounds. For example, we have seen that mono insertion product, bi-insertion product, and also mono insertion CO2 adducts which are present during the solution. So from that we could assign this particular chemical cycle. And you all know one more thing I want to tell you to DST, MSc students. What is the normal oxidation state of carbon? Normal stable oxidation state of carbon? +1, +3, +4, +5, what is it? +4, right? +4 is the stable normal oxidation state of carbon. If you reduce carbon +4 to carbon 0, simply carbon 0, right? Such kind of compounds are highly reactive, right? Can you do that kind of things? Now people found out. People have isolated such kind of compounds. You can see here it's not we isolated, we just prepared as per the reported procedure. You can see here, this is the carbon 0. If you are making carbon 0, carbon's valence is 4. So you are reducing carbon +4 to carbon 0. Means you are creating 2 lone pair of electrons, right? If you oxidize, becomes a carbon 4. You are reducing to carbon 0. Carbon 0 with 2 lone pair of electrons on such kind of compound. These kind of compounds are now invented by chemists around the globe. So then what we have done, we have used this kind of compounds again to activate carbon dioxide. So these are highly reactive. They can trap carbon dioxide nicely. That carbon dioxide can sit on this one of the carbon center, right? And these are beautiful, colorful compounds actually. So we are now trying to exploit this complex as a metal-free catalyst for CO2 conversion reactions. So as I said previously, these ligands, these are NHOPs, these are called anerocyclic olefin phosphines. We have exploited their reactivity as ancillary ligands. Do you know what is the meaning of ancillary ligands in organometallic chemistry? So please read it. What are the ancillary ligands? What is the meaning of ancillary? Right. So we have employed these ancillary ligands in ruthenium-based catalysis. We prepared a series of 16 electron complexes of ruthenium using 18 electron rule, right? So these are highly reactive for certain applications. So this is the molecular structure. You can see similar structure. It shows that the phosphine, new phosphine is nicely attached to the ruthenium center. So of course these are colorful compounds. You can see the color nicely there. It's a orange-red solid. So, and we have made both imidazole as well as benzimidazole. As I said, once we have the benzimidazole, these kind of compounds tend to be more stable, so that we can easily work with those compounds and study their utility in homogeneous catalysis. So of course these are a beautiful compound. You can see we wanted to see whether CH2 is there or not using proton NMR. Proton NMR clearly showed there is a broad peak at PCH2 is because 31P NMR is NMR active nuclei. It has a coupling with proton, pH coupling. You see that in this kind of thing. So these compounds were completely characterized. And then we wanted to see whether we can employ them in the CH activation reactions. This ruthenium complex. Ruthenium, one of the greatest metals that is being exploited in CH activation or CH functionalization reactions in industry. So what are those compounds? Let me quickly tell you. Lots of people around the globe used this kind of isoquinoline derivative. These are biologically active compounds. So you can see that if they use this kind of isoquinolines, this ruthenium, cobalt, different catalysts, they do one job. One is that one of this CH bond is getting activated to give the corresponding olefins. It's a olefin, right? So level 1 olefin. Another set of chemistry, if you treat this amide with alkyne, they give you inserted olefin. These are like annulation, right? But this particular catalyst, the catalyst what we have developed, it does both. It does annulation as well as olefination. So it does both jobs in one pot, right? So that is the beauty of this catalyst, right? Normally it doesn't happen, both things doesn't happen in one pot. Means you throw the catalyst, you throw all the starting materials, you get only one set of compounds and it stops there. But this catalyst doesn't stop there. It does both annihilation as well as volatilization and gives you one compound in a one-part manner. That is very interesting in synthetic organic chemistry. So then my student has screened you have to screen lot of conditions which are the better conditions so that you can get better yields, better isolations. You need to do a lot of work. So my student did, you can see that crystal structures also, this is an annihilation product and this is annihilation followed by olefination. Right? This is called CH activation, CH functionalization reactions. So that is difficult to understand for you, but it's a very cool reaction. You can see that. You see, you have a typical primary amine. If you treat this primary amine with alkyne, it first gives mono annihilation product. Means that this alkyne inserts between the C and H bond and gives you the first annihilation product. The moment it forms in a solution, you have a NH and again CH. Same pocket like here. The catalyst doesn't sleep here. It further again activates these, give you another double annihilation actually. It's a very novel aspect. It does double annihilation. But the moment it forms double annihilation and coordination chemistry, you know coordination chemistry, right? Chelation. Chelation is a very good concept in coordination chemistry, right? Chelated compounds are more stable than monochelations because of chelation, right? They have low energy. So then you have created another chelation, CO and CH. The metal complex goes there and it also activates this CH. So it does both. It does double annihilation followed by olefination at these positions. So we did a lot of work to isolate those compounds and completely characterized those series of compounds. So of course this is a complex one to show that how the catalyst can solve the complex substrates also. So we have done that. And what is the catalytic cycle? As I said previously, you need to propose a catalytic cycle, what is happening in this particular reaction. I quickly discuss with you that the catalyst first reacts with copper acetate, gives you the corresponding N-chelation ruthenium complex, that again reacts with copper acetate and gives you the corresponding acetate complex. And in CH activation chemistry, agostic interaction, anagostic interactions, I hope you are read, you are taught. So that immediately forms CH activation product and gives you metal carbon bonded species. The moment it forms in the solution, another alkyne insert between the metal carbon bond gives you another complex metallocycle, right? This is 8-membered metallocycle. These kind of compounds are highly strained molecule. They are not stable in the solution. They immediately undergo oxidative insertion, inductive elimination. These organometallic concepts, as you know this. So it converts, it cleaves away the catalyst and gives you the mono annihilation product. As I said previously, you have another pocket here, the COCH. Again, another equivalent of catalyst goes to this area and again activates that CH bond. And again it follows the same method, and again metallocycle will form here and then rearranges to give the olefination product, right? So this olefination product formed from the annihilation product. So the moment annihilated product forms in the solution, the catalyst doesn't allow that compound to sit. It's again further activates to give the another compound. So this is the beauty of homogeneous catalysis. That's simply because of the catalyst that you use. And most importantly, the ligand you use. We have compared these compounds with literature available compounds, so they don't do the job. It's because of the ligand that we have developed and thus new reactivity aspects. Right. So like this. My last topic is simply I'll finish it off. Another one is that these are colorful chemistry. These are carbenes. You know, anorcyclic carbenes, you all know that these are singlet carbenes, triplet carbenes, right? You are right. Why are they singlet carbenes? Why do you call them singlet carbene? The students, why do you call them singlet carbene? It's because of spin multiplicity, right? 2s plus 1. 2s plus 1 is 0, singlet carbene, 2s plus 1 3, then triplet carbene. What is S? Spin, right? Total spin. So the electrons in the different orbitals, then S is equal to 1, then 2s plus 1 is equal to 3. If one electron, both electrons in one orbitals, total spin is 0, 2s plus 1 is equal to 1. So that's what singlet carbenes and triplet carbenes, right? So triplet carbenes are not stable. You cannot isolate them in the laboratory. You cannot show them. But come to my laboratory, there are lots of singlet carbenes. They are very stable. Not too moisture in here. You can see in the glove box. Because singlet, sigma lone pairs, they are very stable actually. Triplets are radicals, so they are not stable. So like this, you have read that. So we exploit their reactivity. You can see here, these sorry, it's supposed to be here. This is the carbene. The carbene has naphtha-quinone moiety. Naphtha-quinone moieties are biologically active compounds. And because of this naphtha-quinone, these carbenes shows excellent colors. These are dark green compounds. You can see this is the carbene. It's dark green, you can see there. It's nicely like a leaf, right? Some broccoli like kind of color actually, beautiful colors. So it's because carbenes are colorless, but these kind of carbenes are colorful because of this backbone attached to the imidazole. So then what happened? We have used these complexes, silver-based complexes in homogeneous catalysis, again CO2 conversion reactions. So this paper is now currently under revision. So what we did, CO2, again as I said, we need just balloon. Kids will play balloon, right? You bring that balloon, push some CO2 gas and attach to the reactor. CO2 gets absorbed by the catalyst and converts into the corresponding biologically active compound. These are oxozoledinones. Oxozoledinone complexes at taxol. All these compounds have this moiety which are biologically active. So that's what we are interested to isolate that kind of compounds using this class of complexes. And you can see we have worked on silver. Why silver? Why not ruthenium? Why not palladium? Why not platinum or iridium? Those are expensive. We try to avoid that one. Silver is earth abundant, cheap, non-toxic. So these are the advantages of those ones. Now trying to establish cheaper methods, so-called sustainable, right? Sustainable methods, cheaper, reproducible, and those things we try to implement in our work. So we use silver. You can see that this is a beautiful carbene like a cockroach structure, right? So you can see the cockroach-like structure. We have utilized these compounds in some organic chemistry. So then this is how we prepare a series of silver compounds. It's very simple. You take the carbene, throw silver salt, you get the corresponding silver complexes, we isolate them, completely characterize. So we have characterized all those compounds. You can see these are the molecular structures using simultaneous X-ray technique. You can see all these compounds, they show interesting bonding, right? Carbene-carbon, silver, oxygen is a linear bond, and these compounds are completely characterized. You can see here another exploitation of these compounds. For example, you can see the silver is always attached with some ligand. These are sometimes boring. We don't want to have these other ligands attached to the silver. They don't have proper solubility and they're sometimes crazy. We will not get proper structures. How to get rid of them? So what we have done, we have used another silver salt. For example, weakly coordinating anions like chlorides. Chlorides are always attached to the metal center. Can we avoid chlorides, bromides, iodides using BF4, PF6, like now all these as BF6. So we have used this kind of salts. For example, BF4, SBF6, then you can get rid of X minus out of the coordination sphere. And these are beautifully, purely organometallic complexes. Then these, we can exploit them in different. You can see the molecular structure, two carbenes are nicely stabilized the silver center. So then as I said, this is a little bit boring from student's perspective. So then what I wanted to say here, lots of catalysts have been reported, this kind of conversions, but all these catalysts have some limitations. They are not good in certain case, they need a lot of CO2 gas, etc., etc. But this particular one, the last one, you can see, it obeys all these requirements when compared with the reported compounds. So then what we have done, my students Aishwarya prepared lots of optimization reactions and found out this is the best condition. You use acetonitrile, you get very good yield, 91% yield using this particular catalyst. So then what happened? Of course, we screened over 30 to 35 derivatives to show all these compounds can be achieved using this particular catalyst. And some of the compounds are not reported their extra structures. So how do you know whether it's cis or trans or stereochemistry? So using simultaneous X-ray, we can easily determine those compounds and you could be able to manage those compounds crystallographically. And so many times organic people ask, right, is it scalable? Only milligrams reaction, can you make to 1 ton or can you make 1 kg or 500 grams, 100 milligrams and etc. Of course, we don't go that much level because we are not industry. But many times we show that our catalyst can do give better yields. For example, you can see this is 1 gram. You can prepare 1 gram of this compound using the catalyst, which means that the catalyst can give you higher yields, higher scale. This can be scalable. Again, I want to disclaimer that it's not like industry based. But at some level, you can go to 100 milligrams, like 100 grams and etc. Right? So 1 gram scale, you can easily isolate the corresponding compound. And of course, we are doing you can see this is a typical setup. Simple typical setup, you take 2 balloons, attach to the reactor, you get this kind of conversion, the CO2 converts into this one. Then we wanted to know how effective this catalyst, CO2, what level of CO2 it can absorb. It should have 100% CO2 or like an impure CO2 or 50% CO2, 20% CO2, whether catalyst can take only CO2 level from a mixture of gas. So that does, you can see we have used mixture of gases, CO2 nitrogen, CO2 air, CO2 oxygen, CO2 H2, and again from these reactions, yields are very good, which means that catalyst is very reactive to take only the CO2. So that's because of the catalyst that can take up much lower level of CO2 also and converts into the corresponding compound. So that's what you can see, this is how the typical setup that was used. Maybe this catalytic cycle is a little bit difficult for you to understand. Let me skip it. So far, what are the take-home messages of this catalytic cycle are the following. You can see this is low catalyst loading. You don't need a lot of catalyst, right? Very, very simple. 1 mole % is enough. And mild conditions like acetylnitrile, room temperature. You don't need harsh conditions to achieve those conversions. And cheap metal precursors, silver salts. They are very cheap, earth abundant, non-toxic. So broad substrate scope. And you don't need to add any additives. You can see in industry, they add a lot of additives to make the reaction goes faster. So for example, this kind of compound, you don't need any additives. You simply use the catalyst, CO2 gas, and certain external conditions. Okay, so, and the last slide of my work, and we are also utilizing these carbenes in the borohydride complexes. You can see copper borohydride complexes reported, and in a similar manner, we have also reported this naphtha-quinone complex borohydride complex. You can see this BH4. It's a main group metal hydride, right? By using proton NMR and all other NMRs, we have characterized completely those compounds. And you can see this here, this screen is not good. You can see this screen here, you see this compound. In the solution, it is a beautiful, like it shows fluorescence behavior. It's because of the carbene. You see the left side one, without UV light, with your naked eyes, you can see. It's very normal, pale green yellow solution. But the moment you put this solution under UV light, it shows beautiful light. You can see like a cloudy, like a perivial. So like similar one, it shows that kind of fluorescence colors. It's because of the carbene. It's because of the carbene ligand attached to this class of compounds. Okay, and then you can see this differences of these carbenes. If you have an naphtha-quinone carbene and they show nice colors, if you don't have this backbone, they don't show any colors. They're simple white solids. So it's because of the carbene. So then what we have done, we have also this carbene complex is a very good hydrogen source, H2 source. You can hydrogenate some organic compounds. For example, you see these quinolenes can be hydrogenated to the corresponding saturated systems using this complex, which means that this complex is a hydrogen source containing compound, right? So that's work is now going on. So with that, let me conclude my talk with the following conclusions. I hope I could show you the beauty of the ligand design in organometallic chemistry. By designing ligands which are stereo electronically tuned species, you can achieve the desired properties to make some interesting organometallic compounds, main group compounds, as well as some drug molecules. So this helps us to make, this can be started from the ligand design, right? And I showed you that this is the first time of that kind, a phosphine reacts with carbon dioxide or carbon disulfide, that in dual CO2. 2 times CO2 can be activated using this class of compounds. So that is something novel aspect. I could also show you that this class of ligands, several complexes can be useful, and CO2 conversion to the corresponding oxygen derivatives, which are biologically active species. And I also could show you that the ancillary properties of these cationic NHOPs the ruthenium complexes, you can see that you can achieve elimination followed by, right now, elimination followed by elimination in one part synthesis. Right, this is what I showed you. I hope you could get some of this, at least if not all, some of those as much as possible. So with that, I would like to acknowledge my group. So of course here Maksud is already here, my students, and Rajeshri is also here sitting in the audience, and also Jyoti also sitting in the audience. So they will give the talk tomorrow. Please attend, ask them some questions, give them some ideas and etc. Interact with them to know what kind of research we are doing at SERB Berhampur. So you can connect very well with student interactions. Okay, and I'm also grateful. Let me use this platform to acknowledge the funding that I have received from Ramanujan Startup Research Grant, MO Stars, as well as CRG. So these grants were like, we are utilizing our regular research areas. Let me use one more minute with kind permission from the chair. I am from SERB Berhampur. This is Indian Institute of Science, Education and Research. So please, you all are working BSc, MSc. Come out, go for PhDs. Right? We have excellent facilities. Lot of institutes are there. You are from Rajahmundry, so we are very close. ISR is very close for you. Right? 8 hours you can reach SERB Berhampur. So it's very closest to ISR, closest to you all. Explore other opportunities. Go for PhD. Come to SERB Berhampur. You can do internship at SERB Berhampur. You can write to any of our colleagues. And here also my colleague Dr. Rajesh also there from IIT Dharwad. You can also write to him. Go there. Work for one month, 2 months, do internship, expose yourself what kind of research facilities or these ISRs or IITs they do have. And look for opportunity to do PhD. And try to become a great alumni of this department actually. Right. So then can you stop 1 minute the light? I want to show some pictures. Yeah, these are campus. I am not done, just wait. So here is what, maybe it's very boring, I'll finish 1 minute. So here we are exactly close proximity to the seashore area, right? This campus is just close seashore area. You can see the Bay of Bengal. You can walk from here to our campus through the beach. I'm telling you about this very close beach area, right? This is a campus coming up. It's a beautiful campus. You can have different mind setup to do great work on a regular basis. And you can see this is the group right on top, right? So with that, thank you all. And once again, I thank the HOD and principal for kindly to see you all and be part of your conference. Thank you all. I'm very happy to answer any queries, questions, and etc.
Any questions from students or research scholars, please?
Yes, please. Yeah. Yeah. So tell me at the beginning of the talk, right?
Yes, somewhere at the beginning. Yeah, I was just wondering about compound 1 and 3.
Yeah.
So the only difference between 1 and 3 is just the tertiary butyl group.
Yes.
So phenyl is replaced with tertiary butyl.
Yeah.
But if you look at the NMR,
Yeah.
so minus 14 to plus 8.
Correct.
That is quite interesting. Why is so?
Like amines, tertiary amine and secondary amines. But we think that if you put more and more alkyl groups, the basic property increases, but it's not the case. It's because of the steric bulk. How you can reach the lone pair? That is the main thing behind the basicity, not the groups you attach. If the lone pair is more protected by the all groups, it becomes pure base. Although it has lone pair of electrons. Similarly, phosphine also. The steric bulk matters also behind the chemical structure.
I see, because that is just contradicting the point which you explained before this.
Absolutely. Is so bulky.
Correct. And the second question, which is a trivial question, you said you would be using for the N formulation
N-formation.
N-formation reaction.
That there is a lot of carbon dioxide in the environment, we are just using it.
Yes.
Do you just open your flask and then use it, or you use the balloon?
Absolutely not. We need to use
The balloon.
stuff like atmospheric. But I want to disclaimer here. We are using balloon, right? It's almost like atmospheric pressure. We are not using the 10 bar, 5 bar. It's almost like atmospheric pressure, right? We are putting some balloon. It's almost close to atmosphere. Atmospheric oxygen,
Sure.
carbon dioxide.
Sure. Thank you. Excellent talk.
Yeah. Students? No? Okay.
Thank you so much, sir. That is a very impressive and interactive session, sir. So thank you for educating us on method-free CS2 and CO2 insertion reactions and typical CO2 balloon experiments and formulation products, colorful, biologically active, colorful carbene, sir. It's a very educative session, sir. Thank you for your talk, sir.
Thank you so much.
So thank you, Dr. Sureshri Madam, for your wonderful feedback. So really it's an enlightenment session. So that gives a new scope to the researchers, the students of PG courses, to elevate their positions in the organic synthesis. So thank you very much, sir, for your nice presentation. So as a token of gratitude from the Department of Chemistry to host this international event, so it's our traditions and customs to try to felicitate our beloved and renowned scientist, so who came long way from SERB Berampur. So please accept our invitation, sir. Please come out to the dais. So I request all the organizing committee members, our in charge, head of the department, T. Srinivasrao Garu, the organizing secretary. No, sir, please, sir. No, sir, it's a token of gratitude from the Department of Chemistry. So I request all the faculty members from the Department of Chemistry to take part in the felicitation event. So please welcome our beloved renowned scientist, the Agnarayan Garu. So I request other resource persons, sir, please. Ramakrishna, sir, our beloved and respected Ramakrishna, sir. So please come on to the stage. So as a token of gratitude from the Department of Chemistry, it's an honor to try to felicitate this great young scientist. So he is striving a hard to try to promote the research on basic sciences. Thank you very much.
Any participants who are interested to present a poster are requested to go outside and make your arrangements, please. Any students or participants who are interested in poster presentation are requested to make their arrangements outside the seminar hall. Thank you.
So I request all the students to be seated. So don't try to roam here and there. The next technical session will continue. Good afternoon, dear students. So still far we come across with the sessions that has been held from the scientists from SERB Berampur. Now it's the time to invite Dr. L. Rajeshwari Madam from the Department of Chemistry to continue this chairperson and to convey the vote of thanks after completion of this session. So now we have a talk from this eminent scientist, Dr. Rajeshwari Garu. So we'll have a discussion and we'll have an interaction about the tetrazine-based polymers for environmental and biological sensing. It's one of the very interesting topic as on day, and it's the need of the hour also. So really it's a great honor, sir. So we welcome on behalf of the Department of Chemistry in general and from the Government College Autonomous Rajahmundry, one of the oldest college in the entire country, which is having a great academic legacy. So at this platform, now we invite Dr. Rajeshwari from the Department of Chemistry to continue this session.
Thank you, sir. I am Dr. L. Rajeshwari, Department of Chemistry, Government College Autonomous, Rajahmundry. It is a distinct honor to introduce Dr. M. Rajeshwar Rao, sir, a leading expert in the field of pi conjugated materials and optoelectronics. Dr. Rao currently holds the position of Associate Professor in the Department of Chemistry at the Indian Institute of Technology, Dharwad, Karnataka. Dr. Rao's academic background reflects a strong trajectory of international and higher caliber research institutions. Sir completed his PhD at IIT Bombay, followed by a prestigious postdoctoral research at Academia Sinica, Taiwan, and McGill University, Canada. Dr. Rao has more than 60 publications in reputed national and international journals. He has a significant scholarly impact, over 2,300 citations and a H-index of 22. He has received major recognitions including Early Career Research Award and ECR Award, SERB, the Eli Lilly Asia Outstanding Thesis Award, the Quebec Merit Postdoctoral Fellowship, and multiple institutional research awards. Dr. Rao has been highly successful in attracting research funding, securing 10 major grants as a principal investigator. Dr. Rao has also been instrumental in intellectual property development, listing 5 Indian patents. He maintains an active research group. Under his guidance, currently mentoring 5 PhD students, 1 postdoctoral fellow, 1 project associate, and 2 master students. Sir also acted as a peer reviewer for reputed top-tier journals such as a Journal of American Chemical Society, Chem Communications, ACS Applied Materials Interface, and Chemical Society Reviewers. Beyond his research, Dr. Rao has actively involved in academic governance and mentorship. He currently holds the administrative positions of Associate Dean, Gymkhana Clubs and Technology. Previously, leadership roles at IIT Dharwad include Head of the Chemical Engineering Department, Faculty in charge of Sophisticated Central Instrumentation Facility, and Faculty in charge of Sports. So, sir as a frequent invited speaker for scientific poems. Now I invite, it is my honor to invite Dr. M. Rajeshwar Rao, sir, onto the dais and deliver his talk. Thank you, sir.
Thank you so much, ma'am. Can you hear me? Last. Very good. So, at the outset, I would like to thank the organizers for inviting me and giving me this opportunity that I can speak about my research. So, the title of my talk is about using the tetrazine-based polymers for environmental and biosensing. But when I was coming here, so I inquired with one of your teacher to know who are the audience mainly. So I learned that it would be masters and bachelor students. So that way, I would like to go to their level and then speak. So it is very difficult to speak after Professor Dodi has spoken about his research, but I'll try, by my best to put across some interesting chemistry to you. So I would like to start with this question. Do you know who won this year Nobel Prize in chemistry? Do you know? And which area? You do not know, right? It's very important to know. It's very important to know who won and what they won. Okay, because unless until these groundbreaking research was carried out, as a result, they have got the Nobel Prize. So I thought I would first briefly talk about the Nobel Prize winning molecules and then go through my work. So
let's get started. So these three scientists, I don't know if you know or you do not know, Professor Richard, Professor Susumu, and Professor Omar Agee. These three together won Nobel Prize in Chemistry for developing materials called metal organic frameworks. Metal organic, students, you got to focus here, okay? This is the time you should be focusing here, okay? So metal organic frameworks, what they are and what is the speciality of them. So we're going to see, okay? So you know this construction? What is this? Eiffel Tower. So if you see this is basically a construction made out of, steel structure, right? There are iron rods and then joints brought them together. So that's the structure. So metal organic frameworks are also such kind of frameworks which are prepared by using the linkers and the joints. We call them nodes. The nodes here are metal ions. These are metal ions, right? And these are the joints. So you bring them, join them together. What happens? Let's see what happens. So it forms a framework. It forms a framework. It is not just a two-dimensional view, what you see a small box. When you bring them and join, so it will be a three-dimensional structure, extends to a huge, size. What is it? You can see here. Example, I'm just showing you, see? So these are all the nodes. So you see them, these are all the nodes. These are those the connectors, okay? So it grows in the three-dimensional view, creating lot of porous network. See all this, I missed. Is it frozen? Yeah. You see this? So these are all the porous network. So there is a lot of porosity. So is that for a use? Yes. There is a special application of this porous network. So I'm going to show you. So one best example, which you know, a material which has the porous network. Do you know? What is it? Do you know what is it? I'll show you. This. So how many of you have gone to your kitchen and find this? This. We use this in the kitchen, right? What is this called? Scrubber. Yes. So this has a lot of pores. If you have not noticed yet, you can go back and then see it. It is full of porous network and it can hold a lot of water, right? It holds up a lot of water. You just press it so the water comes out. So why? Because the water molecule gets into the porous network and the porous network holds on to it. But this porous structure is too big because you can see it by your eyes, because porous network is so big, and it is usually made with a foam called polyetherates or polyethylene. Okay, so this is a disordered structure and a big large porous network which is of not much useful for some specific applications which we want to have it. Okay, in that line, what these scientists have done is they have created a molecular porous network. Please note, this is a molecular porous network. The network size, the pore size is 2 nanometers, 3 nanometers, too small, but that is key for several applications. The first, the Robson, he has generated a diamond sort of a structure where we can see that this kind of four-armed ligand is connected with the copper ions. These are copper ions. When you bring them together, so what you get is this kind of huge network which resembles the diamond. Okay? But unfortunately, this mob, what he has created, is not stable and gets collapsed. So it cannot keep its porous network. But he was the one who invented this first. And then followed by the Susumu, he created something called flexible mobs. The flexible mobs are efficient. So the flexible mobs are stable enough, and he was able to, use that for a lot of gas separation and gas storage. You can see the picture here.
So this is all the network, the porous network you can see. Yeah, see, here's a porous structure. This porous structure is useful to store up a lot of gas. The application I'm going to talk a little later, okay? And also, when you have this pores equivalent to the, the size of the ions, so some of the ions are gaseous molecules will pass through, some cannot. So that way you will be able to separate them. So you can use for gas storing as well as gas separation, right? And that also I'll speak a little later and at length. And the third in this line was by Professor Omayagi. So what he has done was, he has developed a range of MOFs having different pore sizes. So he has done a lot of work. But if you read about his story, very fascinating. So he works in USA, okay, but he is a refugee from Palestine. He was a refugee, Palestinian refugee. So to save his life, he ran. So his father sent him to USA because there was a lot of unrest. So his father sent him to USA. He went to USA and he became a researcher and won a Nobel Prize. So very fascinating. You can read about his life. Okay. So he has done several MOFs and used it for several applications. Okay. So one of the MOF has the surface area of close to 3,000 meters square per gram. But when I say this number, does it excite you? It doesn't, because you don't know what I'm speaking about. The surface area is the surface on the walls of the, you have the porous network, you have the walls, right? So there is a wall here. So that is all the surface, right? So you know how much surface area this means? You do not know. But just to make you understand, I'll show you. 2,900 meters square per gram is equivalent to surface area of a cricket ground. Would you believe it? A cricket ground. How big is the cricket ground? Right? So 1 gram is your tablespoon of sugar, 1 tablespoon of sugar, which is like 2-3 grams, have a cricket ground size surface area inside it because of the porous network. Isn't it interesting? It is, right? So that's why these materials won Nobel Prize, and they have many applications. Some of them I'm going to flash it for you. Okay, so there are several interesting properties as well as applications. I'll just touch upon a couple of them so that you will be aware what they are for. Okay, so let me show this video. Yes. So Doddi sir was just speaking about saving the earth by capturing carbon dioxide for his 1 or 2 molecules. So I really liked it. But MOFs are already in action, that they can store up huge amount of carbon dioxide and convert them into the useful products. Okay, and they are being into the market sooner, very soon, because it's right, the application is right here. So let me speak some of the applications just to excite you. One is drug delivery. Okay, so I'm sure you must have heard this word, drug delivery. So what is this and why we have to use this? I'm going to give you a simple example. Assume that somebody has a brain tumor and they will have to take a medicine. So if it is a oral medicine, what do? They just take it. It goes to the stomach, right? From there it goes to intestines,
That's where the absorption takes place and then gets into the blood and runs all the way to the head, right? And it starts acting. Now I'll talk about the flip side of it. One, so because you're taking orally, it is going into your blood in the stomach, so there is a lot of dispersion, right? Distribution. It is not just going into the head, it goes to wherever the blood flows. Is the flip side, you don't want it. Where do you want? You want it in the head, but it is going all over. That's a problem. And second, the stability. Not all drugs are stable enough. So however, many of the drugs are very less. By the time they reach the site, so some of them do decompose. And third, the impact, because you are distributing everywhere, so it is not only going to kill the cancerous cells, but also going to kill the good cells. It's bad, right? So your target should be the site. So as a result comes the drug delivery. So how do you do it? You take a MOF, because MOF is a porous network, you introduce your medicine into it. So it is like a box. You lock it, okay? And you give it intravenous, it just goes there to the site. At the site, it releases it. How? There are many mechanisms. One of the mechanism is, pH. You know that cancerous cells have low pH, which means high acidity, right? They are acidic. So you design your MOF such a way that wherever there is a low pH, it just goes and releases it. So where do you have the low pH? It is at the cancer site. So it goes releases it. That's one way of. The other way is you shine a light, so it releases it. Or a third way is you decompose it and your drug gets released. So there are many mechanisms, but what I wanted to say is MOF is kind of a capsule. It covers, protects your drug and takes it to the site and releases it. So you're saved and only cancer cells will be died. Okay, so all those side effects we see, right? I'm sure you must have seen the people who has cancer and those who get the treatment. It is pathetic, so sad, because their side effects are more than what they're actually suffering from. But do they have choice? No choice. No choice. So drug delivery is one of the mechanism or application of MOFs one can use it for. The other one is water harvesting. So water harvesting this is for exciting. It is still far away to become a realization, but this is something interesting. That's why I'm showing up here. That you go into a desert place, okay, or somewhere where there is no water, but you carry a pack of MOF, okay, and you just open it. So it is able to capture all the moisture around it and then gives you water. There's something interesting. So you can see this video I'll show you. Look at this here. See this? Because this porous network, so you introduce a functional groups. That functional group has an ability to coordinate or capture the moisture in the environment. And as soon as you take this, pack and put it in the sun, because now the temperature is rising, it releases the water to give you this, you can see it again. So when the temperature is low, it captures. When the temperature increases, it releases. So you don't need to heat that. You just put it under the sun. So inside the room, it captures it. You take it out and keep it under the sun, it releases it. You have the fresh, clean, potable water. So this is another interesting feature of MOFs. And moving forward, analyte sensing, of course, because you have a porous network, you introduce the functional groups which can bind to a specific analyte. You'll be able to use it for analyte sensing as well. I'm just showing you here for something nitrobenzene. You can see initially it is fluorescent and it quenches off as it come in contact with the trinitrotoluene, nitrobenzene, etc. So it's like it's sensing for explosive. All right. So because these are not my main topic, so I'm just giving you the glimpses. So I'll go quickly. I'm sorry, but I thought it is important for BSc and MSc students to learn this topic. So that's why I'm presenting it. The other one is MOFs for gas storage and separation. So what is the conventional way of gas storage?
We all have LPG cylinders at home, right? So they are pressurized cylinders. So which means you are carrying a small bomb and keeping it home, isn't it? We're all. Because what happens, like if your cylinder is open and you turn on it, it catches a fire, and we keep hearing here and there, right? So, but is there a choice? We don't have a choice. That's why we are using it. Okay, and the other thing, so famous these days, hydrogen-based fuel running vehicles. But you know, so when you use a high-pressure hydrogen cylinder, so it's literally a bomb you are carrying on your car. So you cannot. So, but they're kind of, you know, taking them to the cryogenic temperatures, making the gas into the liquid, and then carrying it. For now, there is no option. But MOFs are there because of this porous network. They will be able to take up these gases and then store inside, and gives a great stability. You don't need to worry about the stability, what we have been worrying for. We don't need. So MOFs can do that. And as well, as far as the stability is concerned, the separation is concerned, so you know how we usually separate, the conventional method, that you have two gases, you cool them, you take them to the cryogenic, so that they become liquids. At the liquid, now you raise the temperature, so to separate based on their boiling points. There's a lot of energy consumption. There's a lot of refinement. So much we have to spend just to separate. Okay? But if I have my MOF, I design such a way that the porous network is good enough to take one through, the other one to stop. So suppose I have a cylinder, I'll just keep it at the mouth of the cylinder, my MOF material I pass through. Like how we do it, our water coolers at home, water purifiers. So we have the cylinder, right? So there is a carbon-based this, right? We just pass through the water. The mechanism of water purification is so simple. So you have a cylindrical candle, you pass your water through, so there is a different layers of your copper that eliminates the particles. Okay, and then you put it through a reverse osmosis, that's a different story. So that way you will be able to separate it. So MOFs can exactly do the job of separation. You see? Many applications. And catalysis, I don't need to speak. Sir spoke. So you take whatever Professor Doddi was speaking, you take that catalyst, introduce right into the network of MOF, and it will act as a heterogeneous catalyst, and you will be able to perform your reactions. So well known. Okay? So that's about the Nobel Prize and Nobel Prize winning MOF materials. They're very fascinating. So I would highly recommend you to go back and read about them. Okay? So here now I will quickly go through my research for next 15-20 minutes or so. I believe that's what I have. So I'll just quickly introduce, but I will try still going to the master's level. I would not be giving too much of technical details. That's not what I wanted to do here. Okay. So organic compounds. Professor Prasad was talking this morning about the starting of the organic synthesis. Very nicely has explained about the history. So one of the branch, as he was rightly mentioning in the morning, was organic materials. So you take benzenes or pi bonds, bring them together, then you will be able to influence the pi conjugation and the delocalization, as a result homo-lumo gap. So which brings a lot of colors, fluorescence, the beautiful things out. So I'll show you here. So this screen is not that great, but you can see it here. So we have, so you have a range of colors, okay, and will be useful in OLEDs, solar cells, and anywhere. So these days the organic materials are everywhere for all sort of applications, including OLEDs. We have been extensively using them, okay. So because of various advantages, I'm not going into the minute details. You have here, there are small molecules where the pi conjugation is limited within the structure, right? But now I take that and I extend the pi conjugation in one-dimensional plane. What happens? The conjugation increases, right? And the homo-lumo gap reduces, and found that they have better properties and better applications, and we call them one-dimensional polymers. Okay? So we develop several one-dimensional polymers and two-dimensional polymers in our laboratory, and we use them for several applications. But one which I want to speak today here is about sensing. Sensing in different areas. Okay? So before I get into, so I will show you about one fundamental truth that we should be understanding. The cancer is a dreadful disease. Okay, nobody would like to have it, because look at this. If the incidences is about 10 millions in a year, the mortality is 50%. So which means it's almost certain that if somebody gets a cancer, that they would be dying. That's what the fact has been. But why 50%? Because many of them are children. The children will have higher rate of survival. Okay, and some of the cancers. But otherwise, some of the cancers are dreadful, that if one get it, will be dying. But you know why? You know why? It's because that the diagnosis is always very late. Okay, every time somebody gets a cancer, you ask what stage, they say third or fourth. Why? I mean, these are the questions we should be asking. Why? Why it is always third or fourth? Why not second or first stage? Because of, one is the fear of in the process, a second, the lack of instruments. So how usually happens, I don't know whether you know or not. I'll just take a simple example. Somebody has, cough. Okay, so do we doubt that we have cancer? Lung cancer? No. We go to the doctor and we tell doctor, I have cough. What does he say? He'll give you 2 weeks ka medicine. He say, yeah, you may be having some, infection. You go take this medicine. He'll go take for 2 weeks and it doesn't decrease. He will go back. And then doctor, he says, okay, let's go get some x-ray done. And he gets some x-ray done, he sees some, blood test, and he says, okay, we'll wait for 2 more weeks. So it looks like, you may be having a serious infection, it will go down, you go. So after a month, this guy starts coughing blood. He will run to the hospital, then doctor says, oh, you might be having a cancer. Let's go for a biopsy. The biopsy is a process, it's an invasive process. Some machine is kept inside, it goes through your throat, to the lungs. It takes a piece of it, a small piece, that will be brought out and sent to the biopsy. Biopsy would take another 2 weeks to give you the report. So by the time the report comes back, it says you have third or fourth stage cancer. So when we actually ran to the doctor on the first day, when he was in stage 1, He's in stage 1. So had he known that he has a cancer, he would have been treated, he would have got healed. But why this much of delay? The simple reason that the techniques what we have today are not competent enough to tell or to test, in a simple way. For example, if we go to the doctor, say that, doctor, I doubt I have, blood pressure, or I have, or even otherwise. We go to the doctor, what he says, first thing what he does is, he'll put the handcuff to check the blood pressure is fine or not, right? And he will ask you to come in the morning and check your blood sugar. See, how many of us has a machine at home to check blood pressure and blood sugar? Some of us do have. Why? Because that's the technology. It was not there 15, 20 years ago. But it is there now. It has become common. It has become point of care devices. They are called POC, point of care. Okay? So, why? Because they're at home and they're so cheap and so easy to test it. Because you pinch, take one drop and you check it. But if we can also get something like this for cancer, for example, so what doctor does, he will do that as a first. You go and say, I have a cough. Okay, before even running an X-ray, he will run your blood test. saying whether do you have a lung cancer or a throat cancer, right? Isn't it much better to have a point of care devices? So that's where our research should be going. That's where we should be contributing. Then only we can be saved from this disease called cancer. Otherwise we cannot be. So in the line, what can be done to avoid? There is something called, that is what? Late diagnosis, lack of awareness, overlapping symptoms, and all that creating the issue. So what we can do? We can find an alternative, having something called biomarkers. So when somebody gets a cancer, there is some chemicals which will be released. They are specific for that cancer. So that's called a biomarker. If I can identify that chemical and develop a sensor for that, we'll be able to check. How it can be checked? But maybe from saliva or blood or maybe urine. It's so easy. You take one drop of blood and you'll be able to check it, right? So in that line, we developed a biosensor for carcinoembryonic antigen. So this tells that this is a antigen, a biomarker, so which tells if somebody has a throat, lung, ovarian, and breast cancer for women. So how do you do it? From the saliva. You take little saliva of yours and put it on this machine, and in 10 minutes we'll be able to tell whether you have any of these cancers or not. So this would be a point of care device. So how we do it? So I will not go much details, but I just wanted to quickly say, so very simple technique. So you take a ITO strip, you coat a conducting RGO, which is graphene oxide. On that, you put an organic polymer. This is where the design went from my lab, okay? So this is with my collaborator who works in electrical engineering. Together we have designed and developed and patented. So this polymer will be coated on this. This, what it can do, so it can bind to a antibody. Antibody meaning, so you have an antigen, right? I was talking about that the marker, the biomarker is called antigen. So I would introduce a exactly replica, one which can bind to, that is called antibody. I take that antibody and coat on it, this Y-shaped one, okay? And you bring this CEA and add on to it, so it will go and bind to it. And when this binding takes place, there is an electronic interactions. Those electronic interactions generates a little current. That little current can be read by the machine. It will be able to detect it. Okay? So this is basically from our saliva. So all this we make it in a kit, a small strip. So we take your saliva, dilute it, put a drop on it. So this is the antigen, CEA. If it is there, somebody has cancer. So once you put it, that will go and bind. You have more, then it will show the reading high, which means he has the cancer. Okay? So that's how. I'm not going into the details. There is a synthetic procedure. We have synthesized various polymers. Okay, all these polymers have been used for the application, and more polymers here. And yeah, I will only go in the application part. I am not going into the synthesis and the characterization. Yeah, you can see here. So CEA concentration that you can sense from as low as 0.25 picograms per ml. Picograms per ml all the way up to 800 nanogram per ml. So for a healthy person, you can see, for a healthy person, how much it should be? It should be somewhere here, 20. So all of us right now has 20 nanogram per ml CEA in our blood, in our body. Okay, if somebody has this, which means 100, 400, 800, which means they have the cancer. So that's how we'll be able to figure out, and we have done it, and we are also doing the clinical, because we are applying in the patients. We are trying to get more data, so we don't want to have any false negatives, which means somebody has it and it shows that it doesn't have it. That's a problem. So we are figuring it out. So as we check more and more, so we'll be able to believe that we can bring this into the market someday. Okay, so yes, all the polymers we have been testing, and then all the polymers have showed very high sensing, which means all of them can be used for the sensing of this. Okay, so there is also a selectivity. So because you don't want to have any other biomarker come and interfere. So we have also checked CIFRA 21, that is for exclusive for one of the cancers. So it doesn't show any effect. You can see it. That shows only 2 or 3 or 3 or 3. So but we have it up to 19, very high for exclusively for CEA, which means it is sensing only the CEA. All right? Yes. So this is the mechanism, how it works. So we have this tetraene polymer. The tetraene polymers have this nitrogen units, so that can coordinate to the N-glycol unit of the antigen, and it can suspend it. So it allows an antenna to stand on the polymers, so that when the antigen comes, so it can interact and generate that electric signal. Yes. So the second one in this line is about environment. So we have been talking since morning about the environment, right? So, but some of the things are really scary. You look at here. So this is called AQI. You know what is AQI? Very good. It's Air Quality Index. See where we stand. So we stand somewhere. Delhi is 153. Some time back the data was taken. I haven't taken this recently, but this is concerning. 153, and Bombay is somewhere here at 100. Typically the good air means you should have AQI less than 50. Less than 50 is good air. But Delhi has 150, Bombay has 100, 100 plus. But if we keep inhaling this, what will happen to our health and lungs? Right? So sad. So we need to have, again, methods, sensors, which can sense them and also determine them, so that we'll be able to eliminate. So in that, in all this, so the main culprit or SO2, NO2, particulates of 10 and 2.5 sizes. So what we have done, we have developed the sensors for NO2. We have chosen NO2 as, so NO2 as the target, and we tried developing the sensors for that. So NO2 is mostly formed because of the industrial, where you use thermal power plants or the motor vehicles. In the motor vehicles, so you have the combustion unit, right? So where the gas is pumped all the time. So the gas consists of not only oxygen but also nitrogen. When this nitrogen and oxygen at the high temperature in the container, which container? The reactive container of our vehicles. So it starts producing nitrous oxide, NO. And once it is released into the environment, so that gets further converted into NO2. Okay, so that's a serious matter. Okay, so in that line, we have slightly modified and used the hydrogen bonding interactions of the tetrazine. In a earlier case, the biosensing, we use the tetrazine, but here is unoxidized dihydrotetrazine. So that can bind and have hydrogen bonding interactions and be able to, hold on and sense better. So I'm not going into the chemistry details, because I just want to take you through the importance and where the sensing is usually used for. Okay, so yeah, you can see this, the resistive sensing. So this sensing is usually done by measuring the resistivity. So you have a 2 electrodes, you have the material, so you apply the resistivity, you measure that resistivity, and you pass your gas on there, which is NO2. When the NO2 interacts with the sensing material, there is change in the resistivity that you measure. So when there is increase, this you can see it here. 150 nanometers, you have a very high change. See, the change is about, response is 60%, but when it is 25 ppm, the response is low. So that way you will be able to tell that what is the concentration of, the nitrogen dioxide, you have it in the environment. So we are able to, develop the sensor, and also selectivity is quite high, even with respect to the ammonia and humidity, so etc. So it found out to be exclusive and selective
for NO2 alone, right? So the sensing is because of the hydrogen bonding interactions, you can see it here. So higher the hydrogen bonding, so you will have higher, this material, the green, which is this, having higher hydrogen bonding interactions exhibited very high, the response, while the other compounds which have lower or none hydrogen bonding, it did not show much effect, which means you have to have hydrogens to show this interaction. Yes, so what we have done, we have extended into the 2D plane now, and that also we used it, and we found that, so even at 15 ppm, we are able to, sorry. Even at 15 ppm, we are able to sense. So that's because of the effect which created by the 2D porous network. Yes. So one last one, but is an interesting one. So I'm going to ask a couple of intriguing questions here. How many of us are farmers here or coming from a farming family? Many of us, right? Farming family. So I come from, my father still works in the fields, my father is a farmer. So I keep wondering that once they do the plantation, I'm talking about the rice plantation, once they do it, and regularly they do the pesticide and fertilizer, they serve them. Why? Because they want to have higher yields, right? And as well, so all the time the farmer would be going around to see the field to have any visual changes so that he can spray the fertilizer, pesticide, isn't it? So the farmer has only one option. That option is going and seeing for the symptoms. By the time that symptoms occurs, there is 30% of damage has already done. 30% of the damage. As a result, he has to apply more pesticide. When he applies more pesticide, not everything is absorbed by the plant. Only 20-30%. Remaining 70% will get into the soil, and because of the erosion, so when there is a rain or when there is a heavy water is used for irrigation, that drains off and goes into the water bodies, and which you and I will be drinking. So this is a cyclic effect. One is farmer has to input a lot of pesticide, and he has lost 30% of his crop already. And the third, we're all drinking contaminated water. So what should be the solution for this? The solution should be, you should be adding or you should be spraying as much as is needed. Isn't it? Only as much as is needed, one. And second, that if you can identify this disease at very early stage, so you don't need to apply much, right? But how do we do it? Not possible, because the farmer has to see through the eyes. If he has to see through the eyes, only when he sees the symptoms, then only he will be able to do something, right? So that is the biggest loss. You can see the crop losses, typically the biotic losses are 15 to 20%. Biotic losses, getting infections, diseases. So abiotic is not having NPK, nitrogen, phosphorus, potassium, and water is about 50% of the loss. But this is a dangerous one, 50 to 20%. So as a result, it creates many issues. All this, crop loss, financial burden, pesticide poisoning, etc., etc. So there has been a thinking by many, and my colleague and myself were also thinking, we came up with a thought that if we can develop a sensor which can be based on the VOCs developed by the crop. Every plant which is outside will release certain chemicals, some gases. So every plant will release certain gases. So our crop also will be releasing certain gases. And when there is a infestation, so now this crop has to fight. So crop doesn't have hands and legs like us, right? So it has only one way, that it will release the chemicals against that the infestation. So, which means it is releasing a new chemical. So if we can identify what is that chemical, right? If we can identify and quantify, we'll be able to tell that even much before there is a visual changes, we will be able to figure out that we'll be able to tell there is a pest, it is going to destroy and inform the farmer. So when the first attack is very trivial stage and the loss is less than 5%, we'll be able to identify and be able to tell the farmer that you can go and spray. So that way we can save the loss and we can also protect the environment. So with that, we have been searching. So this is very premature, trivial. It takes, I'm sure, another decade or two to come into the actual field, because we just began. We are working right now, but it takes a lot of time and lot many pros and cons to work around to get the solutions. But what we have figured out is that the plant releases these kind of chemicals. The prominent ones we found for one of the crop was linalool and methyl salicylate. So this is only beginning, okay? Don't think that they're going to be out in the market soon. No, they're going to take time. This is the first step, a baby step, I can say. But we have begun. We need to analyze many plants and crop seasons, crop timings, and different diseases, and all that we have to combine and then be able to come up with a solution, which takes time. But this is preliminary data and very exciting data. That's why I'm showing you. So these two are the two of the VOCs we found, and we developed a sensor. By that, we have synthesized this vanillin-linked violozin polymer by using this violozin sort of material, condensing with the trialdehyde to get this polymer, okay? And look at the sensing. So we have linalool. We could see that the response for about 269, we started with 50 and went up to almost 270 ppm. We could see very high response. That's a good news. And as well for methyl salicylate, the value is quite high. So it's about 1000, but I mean that is impractical, I agree, but it takes time to get down. But positive news is that it also shows the change in its, the response time. So that way we are also able to sense. So these are very preliminary, but gives an understanding. So we could also successfully reproduce, at 269 for this, we could clearly see. So the response is on, it is not dead. For methyl salicylate at the high ppm, we could still see the response is positive, that it is not a fluke data, but it is indeed the real, right? So to sum up, so we have developed, I have showed you 3 different sensors. One is biosensor, which can sense CEA, carcinoembryonic antigen, so just from the saliva. The second one was NO2 sensing, so environmental protection, and the third one was the crop health monitoring by sensing methyl salicylate. Okay, so we not only work on that, we work on several pi-conjugated systems. They are fluorescent, the sensing, solid state fluorescent, and etc. In the white light emission. They are the recent publications. So I have, based on the the title of this conference, I have chosen that work to present, but otherwise we also work on electronic materials as well. So this is my group, and I would like to thank, so SERB and the BioCVTH, ICAR for this funding, generous funding, so that we can carry out the research. And so this is a glimpses of our institute. Definitely this is not as beautiful as Barampur, because that's there right on the bank of the beach, but so we don't have bank, I mean we don't have sea, but I'll tell you. So the place where I come from is right at the edges of the Western Ghats. So the weather is so beautiful, so it always feels cool, cozy, nice. You never feel like working, but rather resting. Okay, I would invite you, please come and visit our place. It's very, very beautiful. So there is no ACs. We don't have air conditioning there. We don't need air conditioning. So such is the environment there. It's so beautiful. I invite all of you and master students, you can come over for internships and you would definitely love it. Okay? Yeah, so these are the hostels, main buildings and etc. So with this, I thank you and thank the institute for this opportunity. If you have any questions, I'll be happy to answer.
Thank you, sir. Thank you, sir, for highly informative and thought-provoking talk.
Thank you so much.
Sir, presentation include Nobel Prize winning molecules 2025, molecular organic frameworks, and its applications in different areas. And his delivered talk on his research work, semiconducting organic polymers and for environmental and biological sensing, different biosensor applications, particularly in carcinoembryonic antigen, sensor for monitoring the pollution, tetrazine polymer as a NOT sensor. Thank you, sir. Thank you for your valuable presentation for students and research scholars. Once again, thank you, sir. Now it is a time for questions from participants, students and research scholars. Any questions?
Please.
Sir, that's a wonderful talk.
Thank you.
So you are discussing about the biosensors where you are using RGO, right? And what is the role of RGO there? Like it is a kind of semiconductor it acts as?
No, RGO is a conducting material.
Yeah.
So tetrazine is a semiconducting.
Okay.
So what we want is the tetrazine sits as these islands, and on that you use the antibody. So now there is an antigen and antibody interaction. There will be some electrical signal generated. That will be passed, communicated by the tetrazine to the base RGO.
Okay.
So now RGO can efficiently conduct and help in quantifying. So if you use tetrazine in that place, this is being semiconducting, so it is not efficient enough. So we need the conducting material so that even the tiniest changes you will be able to get.
So the conductivity of ITO itself is not sufficient?
No, we scraped off the ITO. There is no ITO.
Okay.
So we scraped off. It is only the glass.
Right.
That's a good point.
Yeah.
We scraped off the glass.
So it's me, Rajesh. Very interesting talk, Rajesh. The way you have delivered about MOFs and then nicely connected your group chemistry is really excellent, and congrats to see beautiful molecules which has relevance to society. Very nice, all the best. So I always wonder that this MOFs drug delivery. So of course the drug is inside the MOF. That is the main thing that cures the disease. But MOF is also a metal-based or cough-based and metal-based, right? This can destroy or this can bring other effects, right?
I got the question.
So how this will be avoided?
Yes. So there are two ways of looking at it. One is you can choose a metal which is not harmful. So that will be eliminated by the body, one. And second, we can also choose a metal which actually required by the body.
So it will stay inside.
So,
it will stay inside the body.
And it will serve your body. So this can be the other way of.
But the ligands attached to the metal.
Yes.
What about those ones?
Correct. So that would cause a problem. But what we have to look at it is always the chemistry is the pros and cons. Now you take a drug which disperses all over your body and creates the side effects versus that minimal trivial effects which the organic linker is going to create an issue in your body. It's always, you have to weigh the pros and cons. So that way the marks will be much better compared to the all over body dispersion.
Okay. So this water.
Actually my question is, in our stomach there is also HCl creation. So there is also a possibility that the MOF also release the medicine there also?
Very good question, sir. Really a very good question. So that's why I said, if you carefully listen to my talk, I did not say it is through mouth.
Okay.
I said internal. Okay. So you would be giving it to the blood, not through the mouth. Okay. If you give it to the mouth, it gets opened up here only because very low pH. Very good question.
Okay, sir.
Yeah.
Thank you.
Please. Hello sir, it was nice talk. My question on that part, wherever you are trying to synthesize a biosensors about the plants. Correct. You were discussing about
Sensor for the plant you are talking?
so in that part you are telling we can develop sensors where that disease can be sensible in a very early stage. So my curiosity is that can we develop such kind of sensors where we can identify the disease as early stage, as well as we can also identify the conditions, because plants are releasing the chemicals based on some conditions, because nowadays we are moving toward the natural products for the synthesis of drug. So that would be very
That's the exact idea. Yeah. When I began talking about my topic and said it's going to take a decade or two, that's the basic idea. Yeah. That we should be able to figure out. We should be able to figure out what disease is it, at what stage is it, right? So what chemical is it releasing it, and what is that we should be applying it. And that's how we can control that. Yes, that's the idea, the big idea, but it takes time. Okay, that's the idea.
Thank you, sir.
Yeah, thank you, sir.
Any more questions from audience? So thank you very much, sir, Dr. Rajeshwar sir, for the insightful and inspiring talk. Now it is a time to honor to express our gratitude Dr. M. Rajeshwar Rao sir for gracing this conference with his presence as a symbol of our appreciation. May I request the dignitaries and organizing committee members to present a token of felicitation to Dr. Rajeshwar Rao sir. Please request all the faculty members and the research scholars come on to the dais and felicitate the Dr. Rajeshwar Rao sir. I request all the faculty members and dignitaries. Sir, please come. Sir.
अरे बाबू मिडिल तीर
Now next session will start.
You are having different polymorphs of tungsten oxides, right? And you are having oxygen deficient or non-stoichiometric oxides, and you are having hydrated tungsten oxides and tungsten bronzes. These are the different classification you can have in tungsten oxides, and that is the speciality of these oxides, so that you can use these materials for various applications, right from the catalysis, sensors, batteries, and everywhere, right? So now we will have an initial look, the polymorphs you can see here, right? The polymers is that nothing but the tungsten oxide is stable in monoclinic state at the room temperature, right? It is WO6 octahedron connected with the corner series, right? And now this gamma WO3 can be stable as different forms and different crystal structures at the different temperatures. If you change the temperature, it changes its phase, it changes its structure, and if its phase and structure is changing, the properties varies. The behavior changes, right? And if you see minus 43 degrees Celsius, it is stable as epsilon WO3. Below minus 43, if you go, and in between minus 43 and 17 degrees, it is delta WO3. And at room temperature, it is gamma WO3. And above, if you go, it transforms into orthorhombic and tetragonal, right? So let's say, by using the same precursor, can you stabilize this monoclinic epsilon WO3 at room temperature? Somehow. If you can stabilize, you can make this material ferroelectric. Right? You can make this material ferroelectric. That is one opportunity we are having. Right? We can see that one example. And other than this, we are having hydrated tungsten oxides. Again, different hydrated tungsten oxides with the change in crystalline water molecules. Right? So all of them can transform into different stages with the temperature, and above 250 degrees it transforms into hexagonal, and finally it comes into the gamma WO3. Right? And again we are having tungsten bronzes as well. Right? These tungsten bronzes are NXWO3 type oxides. Right? They can be normally synthesized using some protonation or zinc HCl reactions and etc. If you can design these materials with the less chemical impact, that is also sustainability. So we will discuss about one aspect of this one as well. Right? So from the beginning, let's say we will start with a case study, that is development of W18 O49 nanowires and nanocrystalline cubic is 0.5 WO3. Right? This is a simple experiment. If you see, like this experiment, what we have done, we have taken tungsten metallic powder, and we have done the ball milling. Right? So if you do the ball milling, what happens? The defects in your material will increase. Right? What are the defects? Let's say these are solid state materials. That means they follow a certain crystal structure. It follows BCC. The tungsten is BCC. Right? And if you see the most close packed system, that is FCC, if you see in a fruit cart, if you go in a fruit cart, if you see the fruit vendors arrange apples or oranges in a cone shape, if you see pyramid shape, right? That is nothing but FCC, face-centered cubic, and that is the highest possible efficiency you can get. You can arrange spheres with the less spaces in between, right? So now, if you give some pressure to that pyramid, let's say, what will happen? All the oranges gets disturbed and the structure will change, right? The similar thing happens here also. When you hit this material with balls, what will happen? The structure will get disturbed so that it will form boundaries inside, that is extra boundaries. That is called nanocrystalline nature in your material. Right? That is called nanocrystalline nature in your material. And these nanocrystalline nature and increased boundaries in your material, that changes your properties now. Right? If I say a simple example for this one, right? If you have taken a copper wire and you measure the conductivity of that copper wire, let's say it is having some X value, right? And you just do bending for 100 times, the same copper wire you are doing bending for 100 times, and you are measuring the conductivity now. It goes down, right? The same copper wire you are just changing, what you are doing, you are just doing the bending for 100 times, and you are measuring the conductivity now, it goes down. That is because by doing this bending, that is called plastic deformation, that introduces new defects in your material, that is disturbing your crystal, so that these defects, they will interfere with the electron movement, so that the conductivity goes down. Right? Similarly, if the property is changing just with the defects, that means this applies to every property now. Right? Wherever you are using, that means if you are introducing the defects in your material, it changes. Every property will change. Right? So similarly, what we have done, we have taken tungsten and we have done the milling, right? And we have measured the crystallite size. What is the crystallite size? Usually, like the closest arrangement, right? The periodicity, the least possible periodicity in your material, that is crystallite size, usually, right? And we have measured using the XRD analysis, and I don't want to discuss about this one here, like I don't think, you can understand this, but we have measured the crystallite size now, right? And that means after doing milling, we are having two crystallite sizes. Initial one is higher crystallite size, and after milling, the crystallite size has been changed. And now we have done some experiment, that is heat treatment
at 600 degrees Celsius to the 800 degrees Celsius in water vapor atmosphere. In water vapor atmosphere, right? So now what happened? Material is same. The before and after it is tungsten only, but what you have done, you have introduced the defects in your material, right? And you have done the same experiment on both the materials, but in one case you got W18049 nanowires, in another case you are having other phase, that is H0.4 WO3, right? So the difference is coming because of the change in crystallite size here, right? So using the same precursor, you can design two different materials now, right? So what is the reason behind that one? Like let's say, like we have explored, right? This is the initial W18049. Let's say this is the initial W18049. First we have explored how this material looks normally. It is a powder form you got in your hand, let's say. Like how this powder looks like when you have seen this one in a magnifying lenses, let's say SEM, scanning electron microscope, you see normally, right? You might have heard about scanning electron microscope, right? And when you have went for the scanning electron microscope, if you see, it is looking like a beautiful forest, wires, right? The material has grown, it is having W18049 phase and it has grown into the nanowires, and at 650 degrees Celsius, it has not formed complete nanowires, right? You can see the particles, on the particles we are having wires, but the phase formation is not complete at 650, but 800 it has been formed completely, right? How does that happen usually? How does that happen, right? You can see the tungsten reacts with water vapor, and now it produces WO3 and H2 as the byproduct, and now this H2 again can reduce the WO3 and it forms WO2.72, that is nothing but W18049, right? It produces W18049. So now what is this W18049, right? Normally the tungsten oxide is octahedron that is connected with their corners, right? So when there creates an oxygen vacancy anywhere, if you create an oxygen vacancy anywhere, what will happen? This corner sharing shifts to the edge sharing, because it should compensate the oxygen vacancies there, so that the corner sharing shifts to the edge sharing. So when the edge sharing is coming in picture, if you see, there forms a planar defects. That is nothing but a defect, right? And that leads to the highest possible deficiency it can have. Here is that nothing but the WO2.72 condition, and this is how the structure looks like. Initially it is looking this way, and finally it looks like this, right? And we have seen further the same rod, a single rod we have chosen, and we went for the transmission electron microscope. That is the highest possible resolution you can get. And if you see the one single rod, and you can see the beautiful plane of atoms here. This is nothing but the plane of atoms in your material, the same rod you have seen before, right? And these atoms, you have the atomic arrangement here, right? And now, drawing the lines, you can measure the distance between any two layers here, right? And each layer is nothing but each plane of atoms, and you can measure the distance between these layers. And now you can say the despacing, and based on the despacing, and if anybody knows the basic fundamentals of the Bragg's law, right? So from that you can get the HKL value and what is the plane of this one, right? And finally you can confirm your material, what is this material, right? So this is W18049, that is fine. But why it is going as a rod, why not as a particle, right? Why not as a cube, why not as a sheet? The reason is that the defects here, right? You know that there are ordered planar defects here, right? These are this kind of defects they will form, and finally it will form as this structure, and these defects will create a surface energy differences, right? These surface energy differences creates a competition, that competition leads to the growth into single dimension, right? But let's say, okay, it is going into the single dimension, but how does that is going into the lens, let's say? So that's how, like here we have to understand, like this is the basic crystallography, like the relation between the initial tungsten and the WO3 oxide and the W18049, if you see, right? So in the tungsten, the 110 plane is the most, responsive for the oxidation, and it responds, and it forms the 020 plane of WO3, and that further transforms into the 020 of the W18049, but I don't want to break your heads with this, right? But here I want to say this figure, if you see, now on the tungsten particle, when the water vapor is reacting with your tungsten particle, first it forms WO3 layer. That WO3 layer will get reduced with the hydrogen, which has formed as a byproduct there, and it seeds W18049 there. The seeding of W18049 is happening there. If the W18O49 has been seated there, it looks like this. Let's say the structure is like this, right? And here you have to consider about these hexagon rings here, right? So how do these hexagon rings looks like? Let's say these hexagon rings, and these hexagon rings are nothing but the white region here, right? The white region here. That is nothing but these hexagon rings aligns in direction of the growth, actually. So now what happens? On the tungsten particle, the WO3 is forming, the WO3 is converting into W18O49. Now the water molecule comes and goes through this passage, and the process happens, keep on, and finally the growth happens. Like how long you can do this reaction, that much length it can grow. That's how you can get the W18O49 nanowires here. Right. In the second case, same experiment we have done, but on the post-milled condition now. Right, we have taken again the tungsten, but after milling we have taken and we have done the same experiment, no difference. Right? So normally this is the tungsten again, so you have to get the W18O49 here as well, but we haven't. Right? What happened? At 800 degrees Celsius in the previous graph you got the rods, but you got here the particles, no rods, and these particles are of WO3. Right? And here if you see, at 650 degrees Celsius also there are no rods, and we are having the particle nature here as well, but the phase is different now here. It's not W18O49 at all, it is H0.5 WO3. The initial case was monoclinic, but here it is cubic. That is highly symmetric. The cubic is highly symmetric when compared to the monoclinic, but how come this happens here? That is because of the conditions here. So what changes the milling imports on your material? That is very important to understand here. If you see this figure, this is thermogrametric analysis. This is called the thermogrametric analysis. I think many of you might have known that one, right? If you have taken any material and you are heat treating that one with the temperature and you are measuring the weight differences. Let's say if you have taken tungsten and if you heat treat that one in the open air atmosphere, what will happen? Tungsten converts into tungsten oxide, WO3. That means the weight of your material will increase as the oxygen is adding up, right? So now the same experiment we have done for the both materials. If you see, this is the as received, and we are doing the experiment, and even at the 800 degrees Celsius, the weight increment for this material is very, very low when compared to this one, if you see, right? So now that means the reactivity of your material has been increased after milling, because the size has been decreased. If the size decreases, the surface area increases. If the surface area increases, the reactivity increases. So that means after milling, this tungsten is more reactive. So it gets oxidized very fast when compared to the before condition. Now what is the condition here? Like when the same reaction happens here also, tungsten reacts with the water vapor and it forms WO3 and hydrogen is producing here, and in principle this hydrogen should reduce WO3, but it's not reducing here. Why? Because the oxide formation before 600 degrees Celsius is 100% here, right? 100% here. But it needs, for the formation of W18O49 as per the thermodynamics, you should have the temperature of 600 and above. But before that you are having tungsten oxide ready, that thermodynamically it is not feasible to form W18O49 here. So what should happen there? Now hydrogen is going into the lattice of WO3 and it is forming H0.5 WO3 this way. Right? It is fine, the system is having the tungsten oxide, but it is not able to reduce to W18O49 because of the equilibrium conditions are not there for the W18O49 formation. Right? So if this phase has been formed here with a simple experiment, but normally you have to use, I think, zinc HCl reaction or any protonation conditions, or with high chemical experiments you have to produce this phase. But normally we could produce just by changing the initial precursor material, just importing certain changes to the initial precursor material. Right? And the next one is, there is another phase we have produced with the WO3.1/3H2O. This is an hydrated phase, and here what we have done, we have taken tungsten, again same tungsten, and we have dissolved it in H2O2, right? H2O2 dissolved tungsten, right? Easily, very easily, right? And we have produced peroxopolytungstic acid, and simple experiment we have done, we have taken ethanol and we have done hot applied reaction, and finally we got the WO3.1/3H2O. right? And now the time plays a very, very important role. You are having here two conditions. One is the rod kind and another one is the plate kind, right? You are having, here it's looking like plates and it's looking like rods here with the different times, right? So that means with the time, the growth is happening here, right? And if you see here, the surface area is high for which case? The first case or the second case? The surface is high for the first case or the second case? In which case the surface area will be more? For the rods or for the plates? No, it's not the plates, right? You are having two particles, let's say, the value is same, like if you have a chalk piece in your hand and you have broken it into two parts. Now what is the surface area? You are creating two new surfaces there. You have broken it and you have created two new surfaces. That means the surface area has been increased as you are breaking it. So similarly, as the size is less, the surface area is more. And this plays a very, very important role in the further application. Like now we have understood what are the conditions. Like let's say it has been grown into a plate, and what is the horizontal plane, exposed planes, what is the horizontal plane and what is the vertical plane, right? And we have explored that, and we have used this one for the CO2 absorption, right? We have used this one for the CO2 absorption, and if you see, in the rod's case, it has shown the increased absorption, that is because of the increase in the surface area in this case, right? If you see, these are the different rods we are having. When the rods are coming together, what you can see here is that the rods comes together and you are losing all these surfaces wherever they are meeting with each other, right? You are losing all the surfaces wherever they are meeting each other, and so that you are losing the surface area, that means you are reducing the exposed surfaces, so that absorption also will get reduced here, right? So that's how the material is same. The material is same, but what the difference here is that you are having different morphology, so that morphology is also very, very important when you are talking about the efficiency of your material, right? So now the next one is mechanochemically induced gamma WO3 to delta WO3 phase transformation here. The another condition we have to discuss about, right? So this delta WO3 we have seen in the initial slide. If you remember, delta WO3 normally stable at room temperature or not? It is not, it is a low temperature phase, right? Normally delta WO3, if you want to get, what you have to do, you have to do the sub-zero temperature treatment for your powder now, right, in your material. So when you are going to the sub-zero temperature, then you can get delta WO3, but it is not stable at room temperature, because when you are coming to the room temperature, again what will happen, it turns into the gamma WO3, that is room temperature phase. Here what happened, we have taken the gamma WO3, a simple WO3, and we have done the milling again, the same condition we have done the milling here, right? And with this milling, what happened, we have observed the phase change here, that is delta WO3 it has been transformed to, right? It is monoclinic and it has been transformed to the triclinic. The triclinic is the least symmetric crystal structure. The triclinic is the least symmetric. And now you can see we have confirmed this one with the basic X-ray analysis and the reticle refinement, and we have resolved the lattice parameters here. And if you see, the patterns are same for both, and we are confused whether we are right or not, so that what we have done, we have taken the help of Raman spectroscopy, and here we have resolved that yes, the phase has been transformed to the delta WO3, and it is showing the nanocrystalline nature. You can see here, it is showing the nanocrystalline nature, and with the average particle size, the average crystallite size is 11 nanometers. It is having the average crystallite size of the 11 nanometers. And now, how does that transforms actually? This one, like when you have done when you have exposed your material to the ball milling means it is, heavily, collided between the balls, so that there produces the lattice strain, right? It produces the compressive strains on your material. Because of the compressive strains, your atomic positions will differ from the original positions. When they are changing their positions from the original, then that transformation happens. And here also again, the 0, 2, 0 plane is more responsive, and here you can see this is the initial case, the gamma WO3, and this is the final case, the delta WO3, and here you can see the distance between these two atoms
is less when compared to this one, right? And similarly, the distance between these two is getting reduced for the delta WO3. That is nothing but your compression. Here the compression is happening, and at the same time in the above direction it is extension, that is tension, right? So ball milling induces the compression strains on your material that leads to the phase transformation in your material, right? And further we have seen how this transformation happens, and at the same time we have done the XPS to understand there are any vacancies that is contributing to this phase change, right? So and we understood that there are a significant amount of oxygen vacancies, that is 1.3% from the XPS we have confirmed. And now the transformation is fine with the milling, right? But why the phase is stable still at the room temperature? That is because of the oxygen vacancies present therein, at the same time the crystallite size effect, right? The reduced crystallite size and the oxygen vacancies together, they can stabilize this phase at the room temperature, right? And in general it is very, very difficult to stabilize this phase at room temperature, but with this little or simple experiment we can stabilize this phase at the room temperature. And this is my final topic, and I will conclude with this one, right? And this one we are currently working on, and that is nothing but the vanadium induced anomalous low temperature phase stability in WO3, right? And here we have seen delta WO3, right? And even we could stabilize minus 43 degrees Celsius phase at the room temperature now, right? So how could that possible? Minus 43 at room temperature, by doing the allovalent doping of material there, right? We have taken vanadium and we have doped or alloyed vanadium in the tungsten oxide lattice. By doing this one, it stabilizes this phase at room temperature, right? And what and how you can do? Let's say we have done the 3 experiments, and I don't want to reveal like how we have done this one, right? Initial case we haven't added any vanadium. So without adding vanadium, the phase is gamma WO3 completely, 100%. And we have done the reticle analysis and we have extracted the data. And now, then when we have added a little amount of vanadium here, a very little amount of vanadium here, and the ratio of 4:1, here what happened, the epsilon WO3 phase has been increased to 46.4%. Right? The stability of epsilon phase has been observed 46.4%, and even we have increased the vanadium content. Now the phase fraction has been increased to 59.4%. Right? With the vanadium increment, the phase fraction has been increased to 59.4%. At the same time, we have observed V2O5 also here. That means vanadium cannot completely transform gamma WO3 to the epsilon WO3. It has some limitation, and over the limit, it is transforming into the V2O5 again. Right? And further, we have done beautiful TM analysis. You can see the particles here. You can see they are epsilon WO3 particles emitted with vanadium there, and you can see the head of imaging here. You can see various elements how they have been distributed here, right? And here also you can see the interlayer spacing. You can see here, like let's say we are able to see that is like you eat normally wafers like lace wafers. If you see there, you will see the lines on the potato chips, right? It is looking like the potato chips and the lace you eat normally, right? And similarly, you are also able to see here the same lines. Those lines are nothing but plane of atoms. Those lines are plane of atoms, and you have taken your material and you have done this experiment in a transmission electron microscope, and you can see the plane of atoms, and now you can measure the distance between these two consecutive planes, and you can say the interlayer spacing, right? The interlayer spacing, and from that you can get the information, crystallographic information. And sideway, if you see the elemental distribution, you can see how the tungsten is distributed, how the vanadium is distributed, how the oxygen is distributed, and the distribution is even everywhere. It's not, there is no segregation. And some portions you can see these circles, and here you can see the more vanadium. That means that is nothing but the excess V2O5 there. That is because of the excess amount, right? And further we have confirmed this one with a Raman spectroscopy again. Like we have confirmed this one, like the phase is confirmed, and that is because of the vanadium inducing effect. And we have done the XPS analysis as well further to understand any vacancies are there, right? So now, how this phase transformation is possible? That's the question. right? How this phase transformation is possible? Because in the initial case and the final case, if you see the unit cell volume is very, very high, right? The unit cell volume is nothing but the basic fundamental unit of the crystal that forms, right? For the FCC, if you see, the effective atoms are one normally we say, the similarly here monoclinic. The monoclinic is converting into another type of monoclinic, that single unit cell is breaking into 2 unit cells here. So how is that possible? Vanadium is going into the tungsten oxide lattice. Vanadium's valence is V5 plus and tungsten is W6 plus, right? That means in the WO3 there are already existing certain vacant positions. That means locally the tungsten oxide exists as W5 plus. Wherever it exists as W5 plus, there is a chance for the, position for vanadium there. Because V also in the 5 plus state, so it can go and settle there, right? And now also other than that, this V5 plus go into other sites as well, where it will create extra oxygen vacancies there. So now once the V5 plus is going into the lattice, but where it goes, that's the question, right? So we are having this hall, right? This is a unit cell, let's consider. It is, this wall is one plane, this wall is another plane, that is another plane, and this is another plane. And there is another plane we are having, that is diagonal plane, right? So you are having in the unit cell also these many planes, but vanadium goes where? To the 0 to 0. The 0 to 0 is most active plane in the monoclinic. So the 0 to 0 plane is nothing but this wall. It can accommodate, whenever vanadium comes in, it can accommodate, right? Because it is welcoming vanadium. But what happens when the excess amount is coming in, but other planes cannot accommodate that one. Vanadium, this plane can take the stress, strain it can take, but other planes cannot take the strain. Then what happens? There happens a cleavage, the breakage. Because of the excess strain in the 0 to 0 plane, there happens a breakage diagonally. This breakage leads to the formation of 2 other unit cells here. This unit cell is nothing but epsilon WO3. That means from the gamma WO3, epsilon WO3 is being evolved because of the strain that is being caused by the vanadium, and that cannot be taken by the 0 to 0 plane, so that it is breaking in the 110 plane, right? And that is leading to the formation of a new phase, that is epsilon WO3, right? So this is a only phase in tungsten oxides that can be ferroelectric, right? And other phases are not at all ferroelectric. But if you want to make this one ferroelectric, and you cannot produce that one, because the limitation, like you cannot stable this phase at the room temperature by any means, right? Because that is stable below minus 43 degrees Celsius, right? So now by doing this simple experiment, you can stable this phase at the room temperature, and we have, patented this one, and we are waiting for the generation, right? And I will conclude with this, the summary and the feature scope. If you see, we have discussed a very simplistic approaches for the phase and structure tuning in tungsten oxides, and the nanocrystalline nature of the precursor can lead to the different formation pathways and the phases. We have seen like same tungsten we are having, but we have done the simple changes in the microstructure so that you can produce different phases, right? And the mechanochemical approach and allovalent doping in gamma WO3 can stabilize the low temperature phases at the room temperature, right? And now the methodologies can be implemented or adapted for the other systems as well, right? The same idea can take, and we can explore the same ideas for the other materials as well. And further optimization in the parameters to have the utmost control over the phase, structure and morphology is always welcome, right? And with this I'll conclude. And this microstructure is the microstructure you have seen in the beginning, like nanowires, right? Same nanowires. This is pseudo color, and we have sent it for the competition, and we got second best award in Electron Microscopy Society of India conference, and featured in Microscopy Society of America as well, right? Yeah. And with that I'll conclude. I think I finished early?
Yes, sir. Yes.
Yeah.
Thank you, sir.
Yeah.
Any questions from our audience? Any students, sir? Yes, sir.
I am still wondering if you can go to that vanadium.
This one?
So the title is little confusing to me. You might have spoken about, but I was busy
Yeah,
with
yeah,
something
please,
else.
you
I did
can
not.
ask.
Low temperature phase stability. I mean, is it stabilizing at low temperature?
Room temperature. The phase usually stabilizes at -43. But we are stabilizing that one up to room temperature.
So you are able to bring it to the room temperature.
Yes, we are able to bring it to the room temperature.
But what happens if you go beyond room temperature?
That stability we are testing still, and it is still stable till 250 degrees Celsius.
It is stable till 250
degrees Celsius.
Oh, that's good.
Yeah,
That's
yeah.
good. So what application you think will have
We
by
can
bringing it to the RT and then above?
We can use this one for, gas sensing applications. It is working very well.
Okay.
And at the same time, we can use it for ferroelectric applications.
I see.
Yeah.
So, very interesting talk. Thank you.
Thank you.
Thank you, sir. Any questions or any doubts?
Sir, use the materials that should be used for the storage of energy, electrical energy.
Yeah, definitely. And we are exploring for the sodium-ion batteries.
Okay.
Because lithium-ion battery technology is already exhausted. So we are trying this one for sodium-ion batteries.
Okay, very good, sir.
Thank you.
Any students? I think no questions, sir. And finally, it is my privilege to extend a formal vote of thanks to this session. Thank you, sir, for your delivered an excellent talk on sustainable materials design, phase and structural tuning in tungsten materials and tungsten oxides exclusively. Thank you, sir, for your presentation, provided deep insights into methodologies, phase control, defect engineering, and how structural tuning directly influences the functional properties of tungsten oxides, and examples for their application in some smart coatings or environmental solutions, for example, carbon dioxide absorption, and clearly demonstrated the importance of sustainable material design in today's world. The clarity with which you delivered complex concepts have certainly benefited our students and researchers, sir. On behalf of all the participants, and I sincerely thank you, sir, for your sharing your expertise and enriching this session with valuable knowledge, and also appreciate all the active participants with enthusiasm in the made session more useful. Thank you, sir, and thank you one and all.
Thank you so much.
Thank you, sir. And before concluding the session, I invited the HOD formal honoring this guest, Dr. Bandi Sanjeev Garu.
Now I request, it's time to honor our distinguished speaker, Dr. B. Suresh, sir. Please come on to the stage, sir. I request all our faculty members, please come on to the stage. Sir, please.
Sai Shiva.
Sir, Rajesh, sir. Abhi aaye.
Sir, Ren sir. Sir, Rajesh sir.
Just join us, sir.
So, dear students, you should take inspiration, Suresh sir, Dr. Suresh sir. See how young he is, but see how the work. So, you should take inspiration. Why we arranged this conference? The conference encourage chesavante, sir is very near Kakinada place, but sir working in Jaipur. So, kabatti manam kuda passion ga work cheste, we have a lot of opportunities. In future, you should come here and you have to present. So, like that, you have to grow. So thank you so much, Suresh sir.
Adi sir, please.
సార్ని చూస్తుంటే చాలా చిన్న పిల్ల వాళ్ళలాగానే కనిపిస్తున్నారు. మీ మీద జస్ట్ 1 or 2 years పెద్ద వ్యక్తిలాగానే కనిపిస్తున్నారు. NIT జైపూర్లో సారు అసిస్టెంట్ ప్రొఫెసర్. చూడండి ఎంత కష్టపడితే ఆయన ఈ చిన్న వయసులో అంత పొజిషన్కి వెళ్ళారో చూడండి. ఎంత గ్రేట్ ఇన్స్పిరేషనో చూడండి. జస్ట్ ఒక చిన్న మీ మీద జస్ట్ ఒక సీనియర్ లాగానే ఉన్నారు ఆయన. but he is the assistant professor. He is a doctorate from NIT Nagpur. NIT అలహాబాద్లో he selected as assistant professor. ఆ తర్వాత NIT జైపూర్లో అసిస్టెంట్ ప్రొఫెసర్గా సెలెక్ట్ అయ్యారు. అంటే రీసెర్చ్ అయిపోయి చదువు ఎడ్యుకేషన్ అవగానే వెంటనే ఆయన పోస్టింగ్లో చేరిపోయారు. ఆయన యొక్క టాలెంటు, ఆయన యొక్క కృషి ఎంత గొప్పగా ఉన్నాయో చూడండి. ఇటువంటి వ్యక్తుల్ని మీరు తీసుకోవాలి, మోడల్గా తీసుకోవాలి. థ్యాంక్ యూ.
సో ఈసారి అంతా యంగ్ టీమ్, సురేష్ సార్ కానీ మన రాజేష్ సారు అందరు కూడా చూడండి చక్కగా తెలుగులో పిల్లలకి డౌన్ టు ఎర్త్ అర్థమయ్యేలాగా, రియల్ ఇంతకన్నా గ్రేట్ ఆపర్చునిటీ ఉండదు. సో చక్కగా మీరు అవుట్ సైడ్ అయినా సార్ ఫ్రీగా ఇంటరాక్ట్ అవ్వండి.
నరసింహ సార్ మర్చిపోయింది,
ఆదినారాయణ సార్, ఐజర్ బరంపూర్, CSIR గేట్ క్వాలిఫై డైరెక్ట్లీ యూ కెన్ జాయిన్ PhD ప్రోగ్రామ్స్ అండర్ దేర్ గైడెన్స్. సో చక్కటి అవకాశాన్ని మీరు ఉపయోగించుకోవాలి, ఇంటరాక్ట్ అవ్వాలి సార్ వాళ్ళతోటి. సార్ థ్యాంక్ యూ సార్, థ్యాంక్ యూ సో మచ్. ఓకే సార్. So finally today we are concluding this one. Today completed all these sessions. So tomorrow sharply at 9 o'clock all of you should be here. ఈ రోజు కూడా చాలా మంది ఆబ్సెంట్ అయ్యారు. రేపు కానీ ఆబ్సెంట్ అయితే మాత్రం విల్ టేక్ సీరియస్ యాక్షన్. వీఆర్ అరేంజింగ్ ఆల్ దిస్ కాన్ఫరెన్స్ ఫర్ యూ ఓన్లీ, సో యూ కెన్ మోటివేట్ అవుతారని. సో మీరు ఆబ్సెంట్ అయితే కుదరదు. ఫస్ట్ ఇయర్స్ అండ్ సెకండ్ ఇయర్స్ ఆల్ ది స్టూడెంట్ మస్ట్ అటెండ్ ది కాన్ఫరెన్స్ at sharp 9 o'clock. ఆల్ షుడ్ బి హియర్. థ్యాంక్ యూ. సో ఈరోజు కూడా అటెండెన్స్ తీసుకోవడం జరిగింది, రేపు కూడా అటెండెన్స్ తీసుకుంటాం. రాని వాళ్ళకి మాత్రం డెఫినెట్లీ విల్ టేక్ యాక్షన్. మీకు ఏదైనా ఉంటే పర్మిషన్ తీసుకుంటే కానీ ఆబ్సెంట్ అయితే మాత్రం కుదరదు. టేక్ సీరియస్లీ. సో వైండ్ అప్. థ్యాంక్ యూ సో మచ్. సో డే 1 చాలా సక్సెస్ఫుల్గా ఇనాగ్రేషన్తో స్టార్ట్ చేశాం. అలాగే KR ప్రసాద్ సారు మంచి వండర్ఫుల్ కీనోట్ స్పీకర్. అలాగే తర్వాత లంచ్ తర్వాత కూడా మనం సురేష్ సార్, రాజేష్ సార్, ఆదినారాయణ సార్ వీళ్ళందరి సెషన్స్ కూడా చాలా చక్కగా అద్భుతంగా ఇన్నోవేటివ్గా జరిగాయి. ఇదే స్ఫూర్తితోటి, ఇదే ఉత్సాహంతో మనం రేపు కూడా మనం యొక్క కాన్ఫరెన్స్ని గ్రాండ్ సక్సెస్ చేసుకోవాలని తెలియజేస్తున్నాం. థ్యాంక్ యూ అనడాలి. And faculty come for group photo today's session for day 1. మరి మెమరబుల్గా ఉండాలి కదా day 1. అది బాబు వెళ్ళొద్దు అమ్మాయిలు. అలియా ఎక్కడికి గ్రూప్ ఫోటో అని చెప్తున్నాను కదా, రండి. రీసెర్చ్ స్కాలర్స్ ఆల్సో ప్లీజ్ జాయిన్ విత్ us. వంశీ నవ్వడం కదా, పైకి రండి అందరూ. ఆల్ స్టాఫ్, ఆల్ కెమిస్ట్రీ ఫ్యాకల్టీ ప్లీజ్ కమ్ ఆన్ టు ద dais for photo session. టుడే ఎర్రబాబు ఈజ్ వెరీ బిజీ విత్ ఫోటోగ్రఫీ. మరి ఎలా వచ్చాయో మరి ఏంటో మరి లెటర్ చూడడం బాగా తీశాడు. వెరీ గుడ్. నా మేడమ్స్, సురేఖ మేడం అండ్ సౌజన్య మేడం, నళిని మేడం, బేబీ నిర్మలా మేడం అండ్ రాజేశ్వరి మేడం ప్లీజ్ కమ్ ఆన్ టు ద dais ఫర్ బ్యూటిఫుల్ సత్యనారాయణ గారు, మురళి అండ్ శివకుమార్ గారు. డెకరేషన్ బియాండ్ ఈ డెకరేషన్ ఈరోజు మనకి ఇంత అందంగా బ్యూటిఫుల్గా ఉందంటే ద మెయిన్ పర్సన్ బిహైండ్ దట్ వన్ ఈజ్ our P. Shivakumar sir. Give a big round of applause to Shivakumar sir.
మీ అబ్బాయి పెళ్ళి కూడా శివకుమార్కి సంకేతం చేస్తున్నావా?
ఆయన ఫిక్స్ వాడుకున్న వాళ్ళకి వాడుకున్నంత ఆయన.
నిన్ను పిండుకున్నాడు
అది మన హెచ్ఓడి గారు తెలిసినట్టు ఎవరో తెలియదు. మరి మన ఆర్గనైజింగ్ కన్వీనర్ శ్రీ శ్రీనివాస్ సార్, ఆర్గనైజింగ్ సెక్రటరీ మన శ్రీధర్ సార్,